Good morning, everyone. Welcome back to the Fire Weather Research Workshop. This is the second day, and Adam Kochanski and I want to welcome you both, or welcome everybody here, sorry. And we're just getting started as participants and attendees are rolling into the room and into the workshop. So I want to summarize a little bit about yesterday. We had a great turnout. We had over 400 attendees at one time watching the videos live and the presentations. And those attendees were from 17 different countries. So it was a great, great audience. And we had a lot of great questions. It was very engaging. So what we learned from yesterday is we're going to try to improve today. We're going to try to engage all the questions so speakers have time to answer the audience questions. One thing that we will be using the Q&A button that's below. And so I'll get to that in just a bit, but I just wanted to welcome everybody as we get started here. We do have a hashtag. If you're into social media, hashtag is Fire Weather Workshop. So let's get to some housekeeping for the day. First, we'll do the agenda. So we've done the introductions. We've got 3 sessions today. The first session is Coupled Fire Atmosphere Modeling Advances. We have speakers talking about the state of the art in fire modeling, or coupled fire atmosphere modeling. And then our second session is on smoke modeling and forecasting with some observations and in there as well. And then we're ending the workshop with a panel discussion with experts that will describe fire weather and wildfire and needs for operations. So it'll be a very stimulating discussion, and we have a great set of panelists. And so let's get going into the housekeeping. So there will be some time, depending on the presenter's timing. You know, we're allowing 8 minutes for presentation and 2 minutes for questions. So there may be time for questions at after each presentation. So please submit those questions to the Q&A button that is on your Zoom bar at the bottom. You should see a little Q&A. And the questions that can't be answered live, presenters will then respond via text or through the chat, or sorry, through the Q&A bar and type their answers. Please be aware that we are recording this event, and we will share the recording via email to those that have registered. So it should be available by tomorrow. And then to the presenters, please say next slide or next point to advance your slides, as those of you that were controlling the slides that have been uploaded already. Okay, so we also have posted the full schedule and speaker bios in the chat, so please access that if you want to see that. Okay, so first up in our session is the Coupled Fire Atmosphere Modeling Advances, session 4. And our first speaker is Branko Kosovic from the National Center for Atmospheric Research. He's the director of Weather Systems and Assessment Program. He's a boundary layer meteorologist that conducts large eddy simulations and turbulence modeling, and has been working with wildland fire modeling and wharf fire development. So Branko, I'm going to let you take it from there.
Thank you, Craig. First, I would like to recognize my colleagues, Tim Giuliano, Amy DeCastro, Maria Fridiani, and Jason Knievel. Next slide, please. So WarFire is a coupled atmosphere wildland fire behavior model. And recently we have implemented a firebrand transport and spot ignition likelihood parameterization into WarFire. These modules are implemented in the fire module in WRF, which is part of physics module in WRF. And this module includes firebrand emissions that are based on fuels that are burning, firebrand lofting, firebrand transport and burnout, deposition, and likelihood of ignition. And likelihood of ignition depends on the state of the firebrand as well as the fuel it's landing on. However, it's only likelihood, it's not a probability of ignition, because there are significant uncertainties in firebrand transport, as you know. So the problem is hard to constrain to get exact probabilities. And the likelihood of ignition has to be interpreted by expert user based on experience. We hope that in the future, as more data about firebrand transport and fire spot ignition becomes available, this problem can be further constrained. Next slide, please. We have also implemented a fuel moisture content data set into WarFire, ingestion of the data set into WarFire. And the data set is a result of a NASA project where we use machine learning to couple satellite observations with surface observations and produce estimates of both dead and live fuel moisture. This data set is produced daily, once a day, based on MODIS observations, and it's shared through our website given below, and historical data shared through NCAR's data archive hub dash. Next slide, please. So I'll say a few words about application of WarFire to one of the recent fires in Colorado, and that was East Troublesome Fire that took place in October last year. And it was second largest fire on record in Colorado. It started on October 14 and underwent an explosive growth on October 21st. Unfortunately, there were 2 fatalities in that fire and a large number of structures that were destroyed. The fire also created a pyrocumulonimbus that rose to 1,200 meters. In the right corner, you can see the perimeter of the fire with red line on the day of October 21st before the explosive growth. Next slide, please. So to set up this simulation, we used 2 domains. The outer domain covered most of the north central Colorado, and it was resolved with 1 kilometer resolution. The inner domain covered about 50 by 70 kilometer domain, resolved at 111 meters. The fire propagation with level set function was resolved at 27 meters. Unfortunately, at that time, we didn't have high resolution rapid refresh output that we usually use to initialize our simulations. So we used the North American model at 12 kilometer resolution. Next slide, please. The simulation started 8 hours before we ignited fire from the perimeter observed on October 21. And it ran until October 22nd at noon UTC. The output from outer domain was created every 60 minutes and from inner domain every 20 minutes. And here on the right is domain 2 that shows the topography of domain. Next slide, please. So one challenge with this simulation was that we had fuels from Landfire data set from 2014 that were updated based on some local observations in 2017. However, this fuel data set didn't include the effect of beetle kill. So we followed the work of Bright et al. And used satellite observations to update the fuel data and indicate where we have beetle kill trees. And the map on the right shows in yellow the fuels that were modified because of the effect of beetle kill. We followed the recommendation of Scott and Bergen from the report that forest areas that are heavily affected by tree mortality can be modeled as /blowdown fuels. So we modified the category 118 with category 201, low load fuel, activity fuel, and category 183 with category 202, moderate load activity fuel or low load blowdown. Next slide. On this slide, you have 2 simulations, one with the original fuels and the other with modified fuels. On the left are original fuels, and we can see that fire spread in that case is significantly slower than when we use the modified fuels that account for beetle kill effects. In yellow is presented the burn area that was observed on October 22nd. And we can see that with the updated fuels, we predict the burn area quite accurately. I should point out that in WarFire simulation, we don't account for any fire suppression. So usually we all predict the burn area. Next slide, please. We have also looked at the effect of fuel moisture content and used the first constant fuel moisture content over the whole area. And then in the second simulation, we used our heterogeneous fuel moisture content maps produced using satellite observations. That's the middle panel. We see that there is no significant difference between two simulations, and that really the major effect comes from accounting for bill kill. Next slide. This fire is significant also because it jumped over continental divide, and along the continental divide, there are pretty much no fuels. So it jumped over the divide and ignited the fire, spot fire, on the east side of the divide that put in danger as the spark on the east side of the divide. And here we have in contours a number of firebrands that are landing in front of the fire perimeter. And as we can see, they're reaching the continental divide. They're not quite going as far as observed spotting did. So there's still more work to do in improving firebrand transport, as I said at the beginning. And however, this system was implemented in Colorado Fire Prediction System that's operational for the state of Colorado. I'll be happy to answer any questions, and here you have my contact if you want to contact me by email. Thank you.
Great, thank you. Raghu, that was fantastic. We do have time for questions. You see the Q&A box. Here's a question. Could you elaborate on how the affected area by bark beetle infestation was determined, please?
So as I mentioned, we follow the work of Bright et al. There's a paper published that uses satellite observations, essentially Landsat, and using machine learning determines the difference between bill kill trees and the live trees, and that's how this be updated the fuel moisture data set.
Another question from Tim Chavez is what is the difference between your model and the coffee model?
WRF model is different mesoscale model, and the main difference, and however, fire behavior parameterization from coffee was years ago and ported into WRF fire. However, after that, we had evolution of WRF fire, and in particular, how the fire perimeter is tracked is very different. In WRF fire, level set method is used. The rate of spread model is the same, Rothermel model. And the other difference is that we have implemented Scott and Bergen fuel model into WRF fire, while originally it had only Anderson model.
Great. There's another couple of questions. Are firebrands in spherical shape?
Yes, at this point, just spherical shape. So this is something that needs further improvement.
Great. And then another question, just wondering why the HER wasn't available during the fire you examined.
I really don't know. HER was not available. Sometimes the periods that HER is not available because I cannot tell. We didn't explore why ANSAT didn't provide for that period.
Great. And we have a question from our panelists. How are bark beetle infested trees treated within WRF fire? Is it considered a dead fuel?
No, yes, it's considered dead fuel, yes. In this, well, dead fuels are modified to account for bill kill.
Great. It looks like their answers, the questions have been answered, and I think we can go on to our next presenter. Thank you, Marco. Okay, it's a pleasure to introduce Theodore Gianaros from the National Observatory of Athens, Greece. Theodore is an atmospheric modeler with expertise in numerical weather prediction. He focuses on development, implementation of operational tools and services for the protection of the environment, life, and property. He leads fire weather research activities at IERSD NOAA, and leads operational support for tactical wildfire suppression activities of the Hellenic Fire Corps. So with that, Theodore, thank you for being here, and we'll let you take over.
Okay, thank you for the introduction, Craig. It is really a great pleasure to be participating to this excellent workshop and to be given the opportunity to present our wildfire-related work over the other side of the Atlantic in the Mediterranean. My goal for the following few minutes is to give you a clear overview of our team's latest research, which focuses on operational fire spread forecasting using a coupled fire atmosphere model. Next slide, please. Starting with the introduction, IRIS stands for a Rapid Response Fire Spread Forecasting System, and its name was given after a messenger goddess of the Greek mythology. The system itself is based on the coupled fire atmosphere warfare model and employs a prototype geospatial database that we specifically developed for the representation of fuels in Greece. IRIS is currently a fully automatic system, which means that the entire execution chain, from the activation of the system to the delivery, to be a rapid response system, since it is able to deliver a 6-hour fire spread forecast in about 20 minutes, while the 24-hour forecast is accomplished in about 1 hour. It is important to note that IRIS was specifically developed to serve as an operational tool that could support the tactical wildfire suppression activities of the Hellenic Fire Corps. In that regard, the system performance is continually monitored and evaluated both quantitatively and qualitatively in order to be able to improve its predictive capability and also derive products and information that are meaningful and of high added value for the officers of the Hellenic Fire Corps. In terms of its history, IRIS is only 4 years old, since its development began in the autumn of 2017. In 2018, the system was pre-operationally deployed and tested, and since the fire season of 2019, it is fully operational. Next slide, please. The activation of IRIS is exclusively controlled by the Hellenic Fire Corps, whose officers have access to a password-protected web application. Through this application, which is basically a Google map of Greece, officers can request the activation of IRIS by simply clicking on the map and entering the coordinates and time of a wildfire ignition. As soon as they do so, a daemon that constantly runs on our computing center launches immediately the execution of warfire. Within the next 20 minutes, the system automatically dispatches the 6-hour fire spread forecast, and within 1 hour, it automatically dispatches the 24-hour forecast. All data are currently provided to the Coordination Center of the Hellenic Fire Corps in Google Earth, KMZ, and TSRI shapefile formats, and both formats were chosen as they could be easily integrated in the operational tools that the Hellenic Fire Corps already use for managing wildfire incidents. Next slide, please. Moving on to some technical details, the first version of IRIS that was used from 2017 until last year was based on the WRF S-Fire model. The domain configuration used included 3 two-way telescopically nested grids that went down from 15 km to 1 km spatial resolution. A fire grid of 100 meter resolution was used for simulating fire spread, and this was primarily dictated by the availability of the necessary topography and fuel data. In particular, IRIS 1.0 employed a 90 meter resolution dataset for topography and a 100 meter resolution dataset for fuels, while it did not include any fuel moisture model. Instead, fuel moisture was kept constant both in space and time throughout the entire simulation. Today, we're moving to IRIS 2.0, which is based on the warfare coupled model. This new version uses a different domain configuration, which allows us to go down to 500 meters for the atmospheric component of the model and down to 50 meters for the fire spread component. This upgrade was primarily possible by increasing the resolution of the topography and fuel datasets we have. In particular, we now initialize our fire grid with the 40-meter European DEM, while we have also increased the resolution of our fuel map. But most importantly, the new version of IRIS will be implemented with a fuel moisture model whose initialization will be carried out using either weather station-based or satellite-based data. Next slide, please. One of the key challenges we had to face when we decided to develop IRIS was the lack of any information about the spatial distribution of fuels in Greece. And in fact, this is a major problem for the entire Europe, as there is no consistent European fuels database available, apart, of course, from individual databases that were developed separately for specific regions. So to address this critical lack of data, we compiled a prototype geospatial database of fuels by reclassifying readily available datasets to standard and custom fuel models. And while this approach may not be the most appropriate for the representation of fuels, it is, in my view, a very good alternative to having no data at all. And further, this approach is replicable and transferable, and thus it could be easily used in any other part of Europe or the world when detailed fuel data are not available. Next slide, please. So as I mentioned in the beginning of my presentation, IRIS was pre-operationally deployed in 2018, and since 2019, it is fully operational. During these 3 years of its deployment, IRIS was requested to provide spread forecasts for more than 50 events shown on the map of the slide, most of them concentrated in the southern part of Greece. Some of these events were pretty significant, burning a lot of acres of land and showing erratic behavior characterized by the development of convective columns and even some pyrocumulus. But among all these events, I believe it is important to highlight a specific one. Next slide, please. So the event I feel it is very important to highlight is the Mati wildfire that took place in summer 2018. This wildfire was ignited by human negligence in the afternoon of July 23, and in about 2 hours, it literally wiped out the coastal residential area of Mati. The aftermath of this wildfire can be only described as a tragedy, since we had 102 civilian casualties and numerous houses and cars were totally destroyed. While IRIS was not operationally at the time of the Mati wildfire, a retrospective simulation we carried out showed clearly that the system was able to capture the erratic spread of the fire, and in particular the time of the arrival of the fire front at a single major escape route in the area, as shown in the map on the right side of this slide. Next slide, please. So as it needs to happen with any operational system, the performance of IRIS is continually monitored and assessed both qualitatively and quantitatively. Without wanting to go into very much technical details, I should say that we have until today quantitatively verified IRIS fire spread predictions for a total of more than 20 wildfires, and the results, which are summarized in 2 published papers, show an overall satisfactory performance. Next slide, please. So in summary, IRIS is an operational fire spread forecasting system that serves the Hellenic Fire Corps since 2019, showing a considerable capacity with respect to providing accurate and valuable forecast guidance. To the best of our knowledge, IRIS is perhaps the first coupled fire atmosphere modeling system to be used operationally, at least in Europe. The development of the system is continued by incorporating the fuel moisture model, increasing further the spatial resolution of the modeling domains, and accounting for wind gusts as fire spotting. But what is most important is that it appears that IRIS has managed to gain the trust of the people who are at the front line of fighting wildfires. And at the end of the day, it is the wildfire managers and the firefighters that have to conclude whether a science-based tool like IRIS is of added value for the day-to-day job. Next slide, please. So just before closing my talk, I feel it is imperative for me to specially thank 2 lieutenant colonels of the Hellenic Fire Corps, Mr. Gouvas and Mrs. Dasiou, for their close collaboration and invaluable feedback throughout the development and ongoing, of course, implementation of IRIS. And with that, I would like to thank you for your attention, and I will gladly answer any questions you may have either live or through the Q&A section. Thank you very much.
Thank you, Theodore. That was fantastic. We do actually have a question. I will read it. Are you simulating any observations to improve the initial conditions from the background fields from the GFS analysis?
No, currently no. We use this is something I didn't mention in the presentation. Iris is initialized with the latest available GFS forecast, and since we would like it to be a rapid response system, we did not do any simulation.
Great. We still have time for a question or two. I'd like to ask one real quick. How often do you run the simulations? Is it every day? Is it twice daily?
Currently, up to the last fire season, we were running the simulation once a day. I mean, we have a wildfire ignition. The system is initialized and runs for the next 24 hours.
Great. Thank you.
You're welcome.
Okay, if you have any other questions for Theodore, please post them in the Q&A box and he can answer them directly. Great. Our next speaker is Joe Chatelain. He's an associate professor at the University of Corsica in France. He's the developer of the Balbi model, which he'll be talking about today. It's a physical simplified surface fire propagation model. He's a co-developer of acceptable safety distance models designed to define firefighter safety zones. And he's also a developer of simplified physical modeling methods to predict fire eruptions occurring. Joe, thank you very much. And here we go. I think we're going to let you share your screen.
Thank you. Thank you, Craig. Do you hear me?
Yes.
Is it possible to share my screen?
Yes.
Okay. Do you see the screen?
No, not yet. Here it comes. Okay, now we see it.
Okay. Well, thank you, Craig, for the introduction, and thank you for the opportunity to be part of this workshop. So good morning, everyone, and good afternoon or good evening for people from Europe. I'm going to talk about fire spread and more precisely, a new way to forecast fire behavior with the Balbi model. Due to several reasons, and the climate change is one of them, the wildfire activity increases around the world, which leads to major impacts on human activities. So decision-making is crucial to face this growing threat, and people involved in firefighting or in fire management need models and tools to support this decision-making and precisely predict fire behavior. Basically, the modeling of fire behavior at field scale can be split up in two types of models: empirical or semi-empirical models. For instance, the correlations provided by Anderson and their co-authors, or the well-known Rothermel model, are very simple and usable under operational conditions, but they are not physics-oriented or very little, and they are difficult and expensive to build because of the large set of field experiments they require. The interest in detailed physical models, for instance, Firestar 3D, WFDS, FireTech, has been growing for about 20 years because this category of models takes into account large and thin physical processes, and then they may be used to understand the physics of the fire dynamics. But they need important computation CPU time, and thus they are not designed to be used operationally. So we can develop a family of models that bridges the gap between the simple empirical models and complex physical models. A simplified physical model allows to incorporate the most important complex processes, but does not have the computational needs of a full physical model. The model developed by Albini is one of the first simplified physical models, followed by Pani and Peterson's. The Balbi model is another example of simplified physical surface fire propagation model. It was derived from simplified physical conservation laws, and it considers average values of the main variables. So we have no partial differential equations to solve. Its development takes into account the main heat transfer mechanisms, radiation and convection, and depends on the triangle of fire, wind, slope, and fuel. The model provides the main physical characteristics of the fire front: rate of spread, flame tilt angle, flame length, flame height, flame temperature, fire front depth, and flame residence time. The model has been tested against 148 shrubland fires from different regions of the world: Australia, New Zealand, Portugal, Spain, Turkey, and South Africa, with very small overall deviations. The model has several advantages: its simplicity and its physics-based characteristic. Moreover, it is faster than real-time and then can be useful in firefighting. Another very important advantage: the model doesn't have any parameter to fit. All the model's parameters are universal, which means that they never change from one experiment to another. And if we want to be fair, as a modeler, I have to point out some limitations of the model. The first one concerns the calculation of the rate of spread, which is solution of a non-linear algebraic equation, and then requires an iterative method. So, and even if we never had, there might be convergence issues. The second one concerns the fuel bed. The better the fuel bed is known, the more accurate is the model. And finally, the model does not correctly predict the rate of spread for an upslope fire under zero wind conditions, because it doesn't take into account yet the airflow generated by the fire, which is the mainspring of the fire spread in this case. Due to its properties, we can develop numerous applications incorporating the Balbi model. For instance, considering the fire management, and this is a work we did 3 years ago, a coupling between Balbi model and the physical acceptable safety distance model developed at the University of Corsica led to the development of DIMSAL, an application for the definition of safety zones width. In the same way, it could be useful for the determination of the distance of no fuel zones around houses, because in Corsica, for instance, this value is set to 15 meters according to experts' judgment without any scientific study. Another application in firefighting concerns its incorporation into a coupled fire atmosphere model, such as WRF fire, which is possible and is in progress. As a conclusion, the question is, what's next? Next, we have to work on the limitations of the Balbi model. We are currently working on a new Balbi model, which has a different structure from the previous one. We have considerably simplified the model. For instance, the rate of spread is now calculated as the max between radiative and convective contributions. So if the error is expected to be a little bit larger, no iterative method is required to calculate all physical characteristics of the fire front. We have also begun the writing of a physical modeling of the fire-induced wind when fire spreads upslope under no wind conditions. In our opinion, this fire self-induced wind is responsible for the sudden and unpredictable change in fire behavior, which leads to an eruptive fire. We will be able to give an analytical value of the threshold slope angle from which eruption will occur. Thank you for your attention, and if you have any questions.
Fantastic. Thank you, Joe. That was great. As we switch over, let's see here. We do have, yes, so here's a question in the Q&A. Is precipitation one of the input parameters for the Balbi model? If not, is that not a weakness of the model?
Well, for the moment, it is not an input parameter, but we are working on this. We are also working on taking into account, maybe I would say more precisely, on taking into account the live fuel. For the moment, for instance, the live fuel moisture content is not taken into account in the model, but the live fuel is taken into account thanks to its fuel loading. In fact, the live fuel loading. But we are currently working on the precipitations, yes, but
Great.
not for the moment.
There's a handful of other questions here. Let's see here. How does your upslope fire model differ from the regular flat terrain case?
It differs because the slope angle is taken into account directly in the model. It's not a correlation.
Is the
So
code
we have to know the terrain slope angle is an input data. In fact, the model has three types of input data: meteorological conditions, I mean the wind, the ambient temperature, also topographical conditions, the terrain slope angle, and the fuel characteristics, of course.
Great, thank you. We've got, there's a couple of different questions in the Q&A. Joe, if you want to, is the one question that keeps coming, is the code available for the new version as well?
The code, it's not really a code. It's in fact, the Balbi model is designed to be the heart of a simulator. So it's not really a code. It's a set of equations. So is available? Yes, it is. The first version, complete version of the Balbi model was published 1 year ago, and we are currently writing the a new publication, which will be submitted in 1 month, about 1 month. So it's as I said before, it's not really a code. It's very a set of equations which allows to compute all the main physical characteristics of the fire front.
Great, thank you. So Joe, there's a bunch of questions in there. We're going to move on to the next speaker, but let's have you answer those directly to the participants.
Okay.
Great, thank you again. Thanks.
Thank you, Craig.
Okay, I'd like to introduce our next speaker and our last speaker for the session, Jean-Baptiste Philippi. He's also from the University of Corsica. He's a CNRS researcher that is focused on methods and code for fire behavior simulation, from front tracking to burn probabilities and deep learning. He's the main contributor developer for the Meso-NH 4-fire coupled fire atmosphere model, and he leads research on Firecaster high performance computing fire atmosphere numerical decision support systems. Bati, thank you very much. Take it away.
Yeah, hello. Hello everyone, and thank you very much, Craig and Adam, for this invitation to speak here. I will present here what we did in Corsica with the team, with Joe, and what was originally the solver for the Balbi model So, and the code is the code for this solver. It's online. It's called ForFire, but yet it's triggered to more problems, and especially what kind of data would you feed this model, and how do you use it? So we work on this Firecaster research program with many partners down in France and in Europe, and especially Météo France and the fire agencies locally, to define how to full chain to forecast fire behavior and fire weather that will be useful to the field, and as well how to get the data. Next slide, please. So yeah, the basic idea was now that we have this nice formula, how do we use it? So how do we feed it? So what we ended up with is an urgent computing forecasting model running only on red flag days on a very limited area. Here it's been tested on Corsica. What you see down under is fine fuel moisture content computed at 600 meter resolution, and we had that every day from 2017, and it's and every 2 minutes output time step. So in order to guess a bit the complexity of each situation in the rough landscape of Corsica, but it's a rough landscape all over the Mediterranean area anyway. So we use the MESO-NH at 600 meter resolution for that, and it's the base run. So it's generating the basic weather inputs for the fire behavior. Next slide, please. So there, after that, the second part of the Firecast timeline is in case there is a fire alert. So in any case, something happens. We already have the weather fields that are computed, and the outputs that we can have in this tool chain is fire behavior. So it's on the top left, so that the fire line computed with the ForFire code using the Balbi model and the evolving Balbi model, which ForFire is just a solver, so it can solve as well the Rothermel model. So people on the field, they try different scenarios of fire cutting and fire breaks, and they eventually have a deterministic or a probabilistic forecast on the right, and they also look at local fire cut, so the very dynamical situation on the 10 meter by 10 kilometer frame, but at 600 meter resolution, and it uses the same color grade as Météo France using locally, so everybody can understand what's happening. In red, it's in here, you can see it's too small, but it's humidity that is under 30%. So it's a very high dry area. It's always pockets that are happening because of the rough landscape. So we run the model with a 5 meter fuel distribution, and the only thing we need is initial fire location. Next slide, please. The next thing is when we have run, and when we do have a reference scenario that it's been tested on just, so it's 20 seconds to run a reference scenario. Then we can run two kinds of coupled models. The first one is just the smoke dispersions running at 200 meter resolution, just to have an idea of where the smoke will be on the ground. This is not really coupling, it's just fire emissions to the atmosphere to have a very quick idea in 1 hour or where the smoke may go very locally. The second one is the coupled simulations that we run with MESO-NH ForFire coupled, which is pretty much the same kind of simulation that you already saw and know, but it's the idea is to run every 3 hours, starting with the reference scenario, and it updates with observation every 3 hours where we have fire intensity. And we saw that such kind of simulation is very important. It's not only for situation where you would guess it would be a wind-driven or plume-dominated situation. You can see in the next slide. We had especially an event, which was a Chervion area. Look down, please. Yeah, where there was very strong wind, but locally where the fire started, it was under the wind. The wind was blocked by a hill or a mountain, and it was a kind of a strong interaction. And the actual fire line did create a convergence line on an area of lower wind, where we had locally a strong convective effect. It did this interaction selected the path of the fire under the wind until the fire head reached the highest wind which just blowed the fire. And without such tool, the complexity of the situation cannot really be guessed, especially locally here. We have a very, not very densely populated area, but very sparsely distributed. So being able to go down to such complexity at a very local scale is important for us. Next slide, please. Another thing that a daily red flag computer forecast enabled us is to be able to run burn probabilities. You had similar projects that have been shown yesterday from TechnoSilva. And we had an approach of, instead of running millions of fire simulations, we trained a neural network with millions of fire simulations. So instead of having just a plain fire weather index, that is already performed down in France, is to have another index that is based on how much may burn in 1 hour if the fire is at this very location. And that is based purely on simulation. You can play the video. I don't know if it's played automatically or it's just, yeah. So on the left, it's a comparison of the actual initial spread index compared to what we have computed with the burning probabilities and the different classes. So this is a kind of output that is generated every day. So it's an 80-meter resolution and at every 10-minute step for 24 hours. So it's about 10 billion simulation, but emulated by the neural networks. Next slide, please. So thanks to that and the fire behavior, down under is running the same Balbi model. So it's or Rosermel model, and it's plenty of simulations. And what we have is automatically taking into account the fuel distribution and because it's based on simulation and also the dynamical aspects. And it's instead of an adimensional number like 98% of FWI, is just the result. It's good because it's in hectares. How much will burn in 1 hour? It's one simple question, and you know that in different fire classes. So fire class F, which is a red area, that means that it's more than a raging fire might burn more than 400 hectares in 1 hour. And the whole simulation for the area, it's about 2-hour computation, and it's also probabilistic forecast. Or deterministic. Next slide, please. So, as perspective, we'll continue to have new versions of the Balbi models and to solve it. We use Craig's and the SJSU data, work on spotting. We hope to work on the national platform, especially into 2021 fire season, and work on optimization of fuel distribution. I want to thank very much the team, and especially the people that have been working especially on this on the numerical aspects, like Yolanda, Ronan, Frédéric, Vivien, that made the neural networks, and Lila, and the people at Météo France, and everyone. And obviously, thanks SJSU for this opportunity to show our work. Well, merci.
Great. Thank you, Bati. This is fantastic. We have time for a few questions. And I'm opening up the chat box. So any questions for Jean-Baptiste? As these are coming in, I do have a question, Bati.
Yeah.
So you said 2021, you're going to have this operational nationally. Is that the goal?
We already have the fire behavior. So operational. What we hope to have is to be able to run the red flag on other area than Corsica. So we hopefully will run it on the Marseille and Marseille-Toulon area in case they are red flag. So running the high resolution fire weathers in order to fill up drive the fire behavior model.
There is a new question. Is this used for gameplay, finding optimal ways of fighting the fire?
The fire behavior, the first thing, like it's yes, they do use it to just to have an overview of what it could, what the fire could do, but it's same as Farsight, but it's very quickly used, and it's helpful to show people, and for the people on the ground to know what kind of actions and what can they expect from their actions very locally, and for that they need the very high resolution the weather fields. So.
Fantastic, that's great. So let's go to our break, and I want to thank all our speakers. If you have more questions, please put them in the chat and direct them to the speakers. I want to thank our speakers for keeping on time. It was a great session. I know it was very short and information packed, but that's what the goal is to provide a platform for everyone to see the current state of research on coupled fire atmosphere modeling. It was quite exciting. So we're going to go to our break, and we'll see you back here in about 6 to 7 minutes. Thank you. Okay, welcome back, everyone. We are right on time, a minute after the hour, and we're starting our next session, Smoke Modeling and Impact, Session 5, for the second day of the Fire Weather Research Workshop. Our first speaker for this session is Adam Kochanski, who is an assistant professor of wildfire meteorology and modeling at San Jose State University, and he's interested in fire-atmosphere coupling processes. He's the co-developer of the WRF-S-Fire and WRF-S-Fire Chem coupled fire-atmosphere model system. And he works on using satellite data, numerical models, and high-performance computing for fire, smoke, and air quality forecasting. Thank you, Adam, and take it away.
Welcome, everybody. Let me quickly just get my presentation going. Here we go. So I will be talking today about smoke modeling with WRF-S-Fire, and I will focus basically on 8 recent advances and some applications of the system. So you had a good overview of the coupled fire atmosphere systems coming from the previous session. So what I'm going to be talking about is that we can basically use those coupled fire atmosphere models also for the smoke predictions. And before I go into that, I just wanted to highlight how those coupled fire atmosphere models work, and in particular WRF-S-Fire. So those type of models, they integrate on one side the weather component and on the other side the fire spread component. So the way how they work is that they use local fire affected winds to propagate the fire through the landscape, and then they compute the rate of spread, released heat and moisture fluxes, and those fluxes are fed back to the atmospheric model. So the atmospheric model can respond to the presence of the fire, and it can start developing pyroconvection, updrafts related to the fire, and things like that. Now, once we know how this system works and if we know how the fire progresses and we can compute how much heat we have, we can also compute the emissions, how much smoke we have, and then we can use this information to feed into our model to carry the smoke around and basically tell what are the concentrations of the pollutants in the air. And of course, one other really important aspect of the whole problem is knowing what are the fuel moisture conditions. So this weather component, it not only provides the winds to the fire spread model, but it can also provide air temperature, relative humidity, and precipitation that then will be using the fuel moisture model then to go to the fire spread model and to compute how fast fire air spreads and how much smoke is being released. So if you have a model like that, what it does, it computes inline propagation of the fire together with the plume rise and smoke dispersion, and you will get something like here on the right side where you see the fire at the bottom, and you see also those updrafts generated by the fire. You see the cloud of smoke, but also you can even simulate other impacts, like, for example, this pyrocumulus cloud that we saw in our forecasts run for the creek fire for 2020. So why do we do that? Why do we want to use those coupled fire atmosphere models? In short, we do that because coupled fire atmosphere models explicitly resolve plume dynamics and the fire weather interactions. So in other words, they compute the plume rise and emissions accounting for the future fire evolution in response to changing weather and fuel conditions. So we have this coupling that is really important for us, and we want that to have good representation of the vertical smoke structure and then also dispersion. So you may have the best model in the world, but as you saw before, I mean, it's not the end of the game because you need the whole system to actually put it to work and to be operational. So here's just a short diagram showing the components of the WRF-FX system that basically drives WRF-S-Fire simulations. And just a couple of important things that you have to have in order to have those forecasts running is you need some information about the fuel moisture that you see here. You need some type of information about the fire activity, either from satellites, infrared perimeters, or user-specified ignitions. And then you have to integrate everything together, provide it into your coupled fire atmosphere model. And then at the end of the day, you can have your forecast posted on the web, and you can tell, okay, what is the PM 2.5 concentration on the ground? What are the winds? What is the fire activity? So if you have something like that, there are two basic applications of a coupled fire atmosphere model. So on one hand, you can just use that to simulate the actual wildland fires, and that's what you see here on the left side. And that's an example of one of our forecasts run for September 2020. And the other application is, as you see on the right side, you may have a prescribed burn, and you can just initialize your model based on your ignition that you want to have for any future day, and just see what's going to happen, what's going to be the situation in terms of PM2.5 concentration, smoke dispersion, and things like that. So those are just general informations, and now let's just dive into 8 new things that we have been working on for this 8-minute presentation. So the first one is initialization of wildfire smoke forecasts from infrared perimeters. So what you see here is that we integrate infrared observations from an aircraft showing where the fires are, and then we use our WRF fire model to run those coupled fire atmosphere simulations, and we post and process the output online, and we generate those animated maps of, for example, PM2.5 concentration. That's great, but not always this method works, because in some cases you just don't have those infrared perimeters. So we often have to do something different. And that leads us to the second thing that we have been working on. So that's initialization of those fires from the satellite data directly. So we use this support vector machine method that Angel was talking about yesterday, and we basically generate those synthetic fire perimeters, and we use those synthetic fire perimeters then to drive our WRF fire simulations, and then we generate the forecast, and we visualize the forecast, and we can just output that on the web portal to show PM2.5, smoke, or whatever else we are interested in. Now, the third thing that we have been working on was integration of the satellite information directly into our web portal. So before we only had MODIS and VIRS detections being a part of our portal, but we just added another one. So right now we also have GOES 16 and GOES 17 satellite detections, and those detections are available directly on the portal near real time, so we can see what the fire activity is at that time. But also we can use those informations in our web controller that we use to initialize simulations. So you can even, just based on those detections, ignite your own fire within this web controller and just start your simulation by hand. Number 4 is new output variables that we added to the model. We were running our simulations last season, and there was a lot of interest in actual vertical structure of the smoke, mostly for aviation. So we added smoke concentrations at different levels, 1,000, 4,000, 6,000 feet, and we also added a visual range. So those are the new variables that you can expect for the next season. Number 5. We added animated fuel moisture maps and fuel moisture observations. So what you see here on the left side, that's an animation of 10-hour fuel moisture, and that's the assimilated 10-hour fuel moisture product from surface weather stations from those 10-hour sticks. And we will be providing those animations directly on the web portal, so you can see the evolution of the 10-hour fuel. Now, on the right side, what you see is another thing that we added. We added integration with the National Fuel Moisture Database. So we are here looking at the actual observations of the live fuel moisture from the National Fuel Moisture Database, and this information will be available in our portal as well. Number 6, per request of our end users, we added the capability to generate automatically time series for the variables that we have in our model. And what you are looking at right now is just a time series generated, for example, for 10-hour fuel moisture, but you can imagine that you can use exactly the same functionality to look, for example, at PM2.5 to decide when would be the best time to go for a walk if you really have to. Now, number 7, we introduced custom ignition paths in our web controller. So before we just had point ignitions, but now we added those custom paths that you can have, or polygons. And what you are looking on the left side is actually a screenshot of our web controller that is used to initialize those prescribed burns, for example. And here you can just draw this ignition, set a couple of parameters, and then if you just press a button, and it launches the simulation on a cluster, and this simulation is then being executed, and it's then visualized and posted on our web portal, and that's what you see here on the right side. So if you look closer, you see this wide zigzag line, and this wide zigzag line, basically it corresponds to the artifacts of this ignition pattern that we just selected. So that was number 7. And the last one, number 8, is mobile-friendly web interface. So we added support to mobile devices. And what you see here on the left side, that's the animation showing satellite detections that you can access on your phone. In the middle one, those are those live fuel moisture observations that are added to the system. And on the right one here is the actual full forecast with the fire progression and smoke concentration at different levels for different domains that you can also access from your mobile phone. So that's everything. Those were the 8 updates for the 8-minute presentation, and I'm ready for your questions. Thank you.
Great, Adam. Thank you very much. That was fantastic. A lot of information. Let's see here. We do have a question from Marty Alexander. Let's see here. Prescribed burns are essentially stationary fires compared to free burning fires. Does your modeling system capture this difference?
Yes, it does. So there are 2 different ways of dealing with those prescribed burns. So number 1 is that, as I mentioned, you can select your own ignition paths depending on what you want. But the second also element is that we have like a bounding box that we can define. So if you know that this particular region within which you will have your prescribed burn, the fire will be contained within this bounding box. So it will not behave like a wildland fire. It will just keep stationary over this area.
Great. Another question. Have you validated the smoke aerosols with observations, and which ones?
Yes, we have. And please stay tuned. The next presentation from Derek Malia will be talking about that.
Let's see here. Can you comment also on model forecast validation activities that you have been working on, hindcast evaluations?
So that's an ongoing work, and yes, we will be looking in particular at a couple of selected fires from last season, and definitely the creek fire will be one of them. We looked at the plume top heights as the first check of our plume resolve dynamics, and we were surprised to see that actually it looks very good, and we saw in the model plume top heights over 12 kilometers, those plume top heights associated with the formation of the pyrocumulus clouds. And we are also working together with Jeff and Lawrence Livermore Lab on looking at the impact of pine beetle kill trees on the evolution of this fire and things like that. So absolutely, yes, that's an ongoing work.
Last question from Steve Kruger. How do you access the WRF web simulator?
So the web portal is available on demo.openwfm.org, and there are all our test instances, and the one called San Jose, that's the one that we used operationally from the last season. And the actual controller for starting the simulations is, of course, password protected, so only our end users and we have access to that.
Great, thank you. Thank you again. Let's move on to our next presentation. If you have questions for Adam, please post them in the Q&A box. Up next is Susan O'Neill from the U.S. Forest Service, Pacific Northwest Laboratory. Susan's an air quality scientist with the Forest Service. She's 20 years of experience in smoke prediction system development. Her research interests include fire emissions, calculations, modeling smoke dispersion, transport, and chemical transformation, and exploring the application of satellite data to smoke and fire. Susan, thank you for being here today, and take it away.
Okay, excuse me, great, thanks Craig, and hopefully everyone can hear me now. So yes, Susan O'Neill, I'm with the USDA Forest Service, and I'm going to talk about modeling wildland fire air quality events and some recent advances, in particular using remotely sensed data. Next slide. So just to put things in perspective and kick things off here, as we know, as we're all very familiar with, 3 out of the last 4 years have been let's see, what California has seen some humongous wildfire activity and also tremendous smoke impacts from those wildfires. And so here we're looking at 24-hour average PM2.5 concentrations measured at permanent and temporary monitors deployed across the state. And so we can see a time series of when smoke impacts were quite large in the hazardous range. And these, the data are color-coded by air quality index. And in particular, you can also see how the different years were similar and different. And for example, in 2018, fire activity kicked up in July. By mid-July, it was going versus, and then had died out pretty much by the middle of September. And then there was again the Camp and Woolsey fires in November. And then 2020 was much different though, where it was actually a very quiet year until about mid-August. And then fire activity took off quite in a big way. So anyway, with this talk, I'm going to focus on the fires that occurred in 2017 in the wine country, in Napa, Sonoma. And then, but the methods I'm talking about, we've also been applying to some studies and work in 2018 as well. Next slide. So with this particular study, this was undertaken as part of a NASA Health and Air Quality Applied Sciences team, Tiger team. And so at the time, and back in 2018, the 2017 wildfires had been some of the most devastating fires experienced by California. And in terms of both, let's see, well, lives lost and homes lost, and then also in terms of the widespread smoke impacts as well. And so these were 5 large fires that were ignited on October 8th, and they burned about 200,000 acres. So in this study, we had 5 major components to our work, and we had over 70 people involved from about 35 different agencies. So it was quite an effort and undertaking that went into this. So I'm going to cover just a couple of the products and results that we got from this study. Next slide. So the first step in analyzing the air quality associated and the smoke impacts associated with these 5 large wildfires was undertaking the calculation of fire emissions. And so we did that using 2 different methods. And so at the time, GOES-16 was pretty newly launched. And so we were just starting to work with the GOES-16 data. And the GOES-16 fire detection data are delivered every 5 minutes, are taken every 5 minutes. And the GOES satellite sits at the equator, and it returns data every 5 minutes for the continental US. And it's at a resolution of 2 kilometers at its nadir, so about 1,000 acres. And so we found that using this data, we could, for our larger and fast-moving wildfires, we could actually look at the fire progression across the landscape. So we wanted to take advantage of that. So we used the GOES-16 fire detection data to allocate. We used that to get our fire location information, and then using the fire radiative power, we calculated fire radiative energy and allocated, integrated that to a 1-hour resolution, and used that to derive daily, to allocate daily emissions that were calculated using the blue sky system to an hourly time profile. And so I want to acknowledge my co-author and co-worker here, Sean Rafuse, who really did a lion's share of the work with this. And so he's been really great. So that was one fire emission data set that we derived. That was for the 5 large wildfires north of San Francisco. For the other fires that were occurring across the state, which in the map you can see in the blue, we used Modus and Veer's fire detections. And we aggregated those detections together, drew a buffer box around each of the detections, dissolved those buffers and then put our own 1-kilometer grid on top of them, and then applied an acre estimate based on vegetation type to then calculate fire emissions for those locations using, again, the blue sky system. Next slide, please. So with those calculation mechanisms, we came up with total fire emissions for the 5 large wildfires and the other fires across California. And here's a time series of what those emissions look like. And so the solid line and the bold dotted line are the fire emissions allocated hourly for the 5 large wildfires north of San Francisco. And so the difference between these 2 curves is that in the baseline case, we're using the temporal profile from the CMAQ system, so the default temporal profile that's applied to fires modeled within CMAQ. And then the dotted line is showing the custom temporal profile derived using the GOES-16 fire detection data. And so as you can see, the first 24 hours, 36 hours of the fires, the two time profiles are quite different. And so it was critical to catch. So the fires started late in the evening of October 8th, and then we're going quite strong into the morning of, the morning of the 9th. And so we see that in the GHOST custom time profile here. And that was critical to capture those first 24 hours worth of smoke impacts. Thereafter, though, what was interesting and actually rather heartening to see is how these two profiles lined up thereafter. So the next 2 days after the initial fire start, the default profile and the custom profile actually lined up quite closely. And then the gray shaded time profile is the profile of emissions from all the other fires across the domain. Next slide, please. And so with those fire emissions were calculated using the Blue Sky system, which is fundamentally a ground-based system, looking at the fuels on the landscape and how they combust, and applying emission factors that have been measured over many years to calculate emissions from the fires for these different fuel types. And so so for these 5 large wildfires, they burned through about 10 major fuel types. And fuel header, and what these figures show, so the left figure is fire area for each of these 10 fuel types based on total fraction, based on the total area. So we get a fraction of the area for each of the fuel types. And then similarly, we have a fraction of PM2.5 emissions for these 10 fuel types based on the total PM2.5 emissions. And what jumps out here is that fuel type, let's see, acres are not necessarily a good proxy for emissions, because 10% of the acres burned were actually responsible for 62% of the PM2.5 emissions, because that 10% of the total acreage were actually in a heavily forested system. And similarly, conversely, about 38% of the total area burned was in shrubland, but shrublands were only responsible for about 15% of the total emissions. Next slide, please. So we had 7 modeled and analysis cases. We had 3 WRF CMAQ runs, and then we applied 4 data fusion and machine learning algorithms to the best performing WRF CMAQ run. And many thanks to the Bay Area Air Quality Management District, who performed the CMAQ runs. And then the data fusion analysis was done by Mohammed Al Hamdan, and then the machine learning methods were conducted by Yufei Zhu, who was a postdoc with our group. Next slide, please. And here's some of the results. And so on the top, we have scatter plots of monitored PM2.5 concentrations versus modeled PM2.5 concentrations. And these are 24-hour average data. The red are data at the permanent monitor locations, and blue are the data at the temporary monitor locations. And so with these results, we can see that there is a high bias with the models. So the top three scatter plots are the WRF CMAQ run results, and the bottom 4 are the machine learning data fusion results. So overall, the data fusion results, as expected, improved on the modeling results. But having these temporary monitors actually gave us another independent data set to evaluate with. And results were very different at these monitor locations for both the WRF CMAQ runs and then also for the machine learning methods. And so actually for the best performing case at the temporary monitor locations was actually the baseline case in terms of mean bias. So the results were much more mixed with at the temporary monitor locations. And with that, next slide, please. And so we also applied health impact estimate using these data, and we used the random forest approach. That was the best performer out of all 7 cases to estimate health impacts. And at this point, I think I'm probably out of time and I should pause. And if anyone has any questions, please let me know. Please contact me. And I also invite you to, next slide, please. Actually go 2 more slides to the acknowledgements. So I just want to acknowledge my co-authors, and I invite you to go to a new publication that's just now coming out in Journal of Air and Waste Management Association on this study and this work. Thank you very much.
Thank you, Susan. That was fantastic. We're kind of running out of time. We're kind of behind, but if there are questions, please post them in the Q&A, and Susan can directly type the answers and respond. It looks like there is one question, but we'll let you answer that, Susan, offline. Thank you again. Okay, moving on to our next talk. I'd like to introduce Derek Malia from the University of Utah. He's a research assistant professor in the Department of Atmospheric Sciences. His research is centered around using atmospheric models to better understand fire activity and smoke dispersion, and he's currently working to improve smoke forecasts within WRF-S fire. Derek, take it away.
Thanks, Craig, and thanks for the introduction and then the invitation. So today I'll be discussing evaluating wildfire smoke transport within our coupled fire atmosphere model, WRF-S fire. And so I won't go through this as Adam mostly went through this in his presentation earlier, but essentially we've been using WRF-S fire to simulate and forecast smoke transport across the Western US. And so WRF-S fire is a really ideal tool for forecasting smoke in that it runs at a relatively high resolution, so we can actually model smoke transport through areas of complex terrain. But also because of the higher resolution, we can also predict or estimate the wildfire plume rise explicitly, and as it explicitly accounts for that within the WRF model. And so with that said, this modeling framework works great and, it looks great, but actually how does it do when we actually compare this to observations? And so there's kind of two aspects to this. There's the plume top evaluation, or looking at the vertical distribution of smoke, but there's also kind of the horizontal aspect, which I'll kind of talk about in a little bit. And so we've actually evaluated our WRF-S fire simulations for several fires across the Western US. Against MISR observations, which is an instrument package that's located on the Terra satellite. And so when you look at the observed plume top heights, you can see that, overall there's pretty good agreement between the WRF-S fire simulated plume tops with the plume tops that are being estimated with MISR, where we see maybe a discrepancy of about 200 meters. So in terms of, resolving pyroconvection, that would be considered pretty good. We've also compared them for the Pioneer fire in Idaho, which in 2016, which was one of the larger fires in Idaho during that fire season. And what you can also see here, once again, is that overall WRF-S fire does a pretty good job when you compare this to the observations as detected by MISR. Here, there is a little bit of a negative bias of about 300 meters, and there's also a little bit more variability in the smoke plume tops in WRF-S fire relative to that of MISR. One thing to kind of note here is that you can see that, the MISR does keep the smoke plume kind of more confined to the fire itself. And what we suspect is going on here is just that the smoke plume kind of becomes more diffuse as it gets further and further away from the fire. And so the MISR plume top, database is just not able to kind of pick up on those plume tops as that smoke becomes more diffuse. But overall, the agreement looks pretty reasonable here. In terms of horizontal transport, we actually looked at another fire that was actually 40 miles southeast of Salt Lake City back in 2018. This was actually Utah's largest wildfire for the 2018 wildfire season. This was also a case where we were actually running WRF-S fire operationally for this specific case. And so over here, you can see these WRF-S fire simulations. You can see the high resolution simulation kind of centered over the fire. And then you can see the kind of more outer domains kind of centered further away from the fire, but you can see that it kind of captures the downwind transport of smoke. And so one reason why we looked at this case study is that the Salt Lake Valley specifically has a lot of air quality data sets that we can look at. So we have, of course, the Utah Division of Air Quality, high quality kind of air quality stations located at a number of spaces or locations across northern Utah. But here we also have our mobile measurement network from the TRAX train, where we have an air quality instrument that's mounted on Salt Lake City's electrically powered light rail train, so it's not generating any emissions or anything of that nature. And then we also have Kerry Kelly's AirU low-cost sensor network and Purple Air sensors as well. And so from this, we can actually resolve the kind of spatial temporal variability of smoke that you often see when you're relatively close to a wildfire source. And so just to give you a kind of brief overview of this event, before the evening, PM 2.5 concentrations across the Salt Lake Valley were relatively low. And then what happened during the evening is that PM 2.5 concentrations ended up spiking. And that's just associated with drainage flow, carrying smoke from the mountains down into Utah Valley and then eventually into the Salt Lake Valley, which is one of the lower elevation locations in the Great Basin. And so as a result, the smoke was kind of pooling up in that area. And so we saw this kind of subsequent spike in PM 2.5 as a result. And then during the next day, you have convective mixing due to the heating from the sun. And so what this effectively did is this mixed out the pollutants from the Salt Lake Valley, while also the wildfire became more active and was able to loft the smoke further into the atmosphere and then evected away from the Salt Lake Valley. And so this is just a simulation of that kind of shows you that kind of diurnal profile. And so the contour areas are WRF fire simulated surface PM 2.5 concentrations. I've also plotted up wind vectors on here as well. And so what you can see is during the nighttime, the smoke gets pulled up into the Utah Valley and the Salt Lake Valley. So I'll kind of rewind this video right here. But basically what you can see is when I reset this, you see drainage flow coming from Spanish Fork Canyon, which drains the smoke into Utah Valley and then subsequently into the Salt Lake Valley. And then as you progress into the afternoon, the smoke plume kind of gets lofted further up and then kind of gets evected to the northwest by, or to the northeast by southwesterly winds. And so when we looked at the observations, what we noticed was that there was actually a lot of spatial heterogeneity to this smoke plume, where we saw higher smoke concentrations located within the middle of the valley, but we also saw lower PM 2.5 concentrations in the periphery of the Salt Lake Valley, which you can kind of see here. And so what we suspect is we have this kind of complex interplay between different mountain valley circulations, where we were having in the adjacent mountains to the Salt Lake Valley, there's no fire actually located up in these mountains. And so what this was doing is this was bringing in or advecting in or draining in kind of cleaner air from the upper elevations. And so that was kind of coming out of the mouths of these mountain valley canyons. And then what was happening here too is that you also had kind of convergence going on in the middle of the valley. And so what this was ultimately doing was kind of constricting the smoke plume to the center part of the Salt Lake Valley. And then, of course, we also have this kind of down valley kind of smoke transport where Utah Valley is kind of at a slightly higher elevation. And this was transporting that smoke down into the Salt Lake Valley. And then, of course, as I mentioned before, this was being kind of constricted by those mountain valley drainage flows from the adjacent mountain canyons. And so what you can see here is in these dots right here, these are actually the air quality observations. And this elevated line is the mobile air quality measurements from the TRAX platform. And so ultimately what you can kind of see here is that, our simulations are able to capture this, the smoke gradient on, the edges of the smoke plume, which is suggesting that WRF Fire Chem is actually able to kind of resolve the drainage flow from adjacent mountain valleys, and also just overall the kind of nocturnal mountain valley circulations that you see during the evening. And so this was really encouraging to see. The model simulation, wasn't totally perfect. I mean, there were some areas where it struggled where, for the larger mountain canyons, we actually got the gradient, which is suggesting that we are getting these kind of finer scale mountain valley circulations or mountain canyon circulations and drainage flows. But there were some other mountain valley canyons where we weren't getting that kind of drainage flow correctly resolved, which you can see here, where the WRF fire simulation, the PM 2.5 was a little bit higher than what was being reported by the air quality sensors located in the valley. But nonetheless, pretty good. And the reason why we don't think we're capturing the smoke transporting these kind of mountain valleys is just that they're too narrow for our WRF fire simulations to actually resolve. They have a diameter of about maybe 1 to 2 kilometers, which, a 1.3 kilometer WRF simulation just won't be able to kind of resolve that kind of drainage flow. But overall, WRF Fire did a really good job capturing the plume tops and also just the overall kind of horizontal smoke transport And that's all I have. So just let me know if you have any questions and I'd be happy to answer them.
Great, thank you, Derek. Let's see here. We're still running behind a little bit. I'm gonna move the questions into the Q&A so we can get on to our next two talks. So Derek, thanks again. And please post questions for Derek in the Q&A box. All right. It's a pleasure to introduce Neil LaRoe, who's assistant professor in the Department of Physics and the Atmospheric Science program at the University of Nevada, Reno. Neil is an international expert in observations of wildfire plume dynamics using radar and LIDAR. And I've had the joy to work with him when he's at San Jose State. And he's also an expert in mountain weather. And when he's not chasing fire plumes, he's usually backcountry skiing when there's snow. So Neil, take it away, and thanks for being here.
Great, thanks, Craig. Yeah, Nevada is not actually a different country, believe it or not. So I don't know if I'm international, but in any case, I'm going to be talking about something a little different aspect of kind of modeling and really, in this case, observing smoke plumes. In particular, what we can infer about some of the dynamics of the convective column and how that feeds back on the fire and even how we can use this information to track fires. So yeah, I'll be talking about radar observations of kind of one of the extremes of fire behavior, in this case, pyrogenetic tornadoes. Go ahead to the next slide, please. All right, so this is a short talk. I figured I'd just jump into the interesting data that we have. The summer of 2020, as most of you know, was a season of superlatives when it came to fire behavior in the Western United States. And part of that extreme of fire behavior was the occurrence of a number of what we consider to be pyrogenetic tornadoes, which are tornado strength vortices triggered by the combination of the fluxes of heat from the fire, as well as the development of deep pyrocumulonimbus clouds aloft. So the first of these cases is shown here. This is the Loyalton fire on the 15th of August, 2020. It's a little bit north of Reno, Nevada, right on the California-Nevada border. And what we're looking at here is a NexRad radar animation of the plume evolution during its rapid deepening that was also the period of vortex generation. And so NexRad radar is a 10 centimeter wavelength radar, and it's particularly good at looking at the structure and evolution of wildfire plumes because it's sensitive to the larger ash particles suspended in there. So the kind of millimeter to centimeter scale particulate matter that's being lofted inside of the plume. So it's not directly the PM 2.5 that's been talked about in some of the previous talks, but it is of course closely related. And that lets us map out the plume structure. You can see those cores of higher red isosurfaces being lofted up in this animation here. And those are the deep convective cores within the plume. We can of course track the plume tops. You can see the triggering of the pyro-CB where the plume top goes up to about 12 or almost 13 kilometers here. Beneath this, what we see from the ground is encapsulated in the two bottom photographs. These are both still images, but if you watch the videos, it's considerably more spectacular. There were two different types of kind of tornadic strength vortices that formed in this event. On the left, we'll have something that I'll call an embedded vortex or vortex pair in this case, which consists of both a cyclonic and anticyclonic component. This is looking back into the fire kind of along the wind. And so the red one is the anticyclonic component here. And that's the one that really contracted and led to significant strengthening and tornado strength winds apparent on the Doppler radar as well. And it's embedded because it's linked to the primary updraft of the fire. So it's embedded with the convection and that deep convective core that you can see coming off of the fire. The second type of vortex that I'm going to talk about is a shedding vortex that's shown on the bottom right here. And that's kind of pendant from the underside of the plume and can actually migrate downstream and away from the fire perimeter itself, so it doesn't remain exactly anchored to the fire. Next slide, please. All right, so we can use these radar data to kind of create an event summary, and that's what I'm showing in the left panel. The top is a radar time height diagram. We can see the plume top heights as they evolve in time. That's that black line along the top. So you can see it goes from about 6 kilometers in altitude up to about 13 kilometers at its deepest point. Everything above the black dashed line is also a pyroconvective cloud. It's above the condensation level. And we can see these deep cores of higher radar reflectivity that we saw in the animation as they loft material up into the cloud aloft. The bottom panel shows the vortex rotational winds as a time series. So the y-axis is the strength of the rotational wind couplet that we're observing, and the x-axis is the time series. And you can see that as the plume goes through this rapid deepening, it develops these stronger periods of rotation, and really a prolonged period of rotation that had up to 4 distinct vortices within it. The image on the right shows one of those vortices. These were all anticyclonic in rotation, which I'll talk about in a moment. And so that kind of red and green couplet right in the middle, that's the characteristic vortex signature. We can also see some other interesting wind signatures in here, including flow splitting. You can see that flow kind of splitting around the head fire, and a pocket of flow reversal coming into the back of the fire. And I'm going to really key on that feature because I think it's an important metric for us to be looking for when we're looking at fire evolution. Next slide, please. Okay, so kind of summarizing this event, we can take all the different vortices that were observed and construct vortex lines. Those are the black lines in the bottom left. And we can place them in the time mean plume structure observed by the radar. Those are those red and orange and gray isosurfaces showing the plume structure here. And we can see all those vortices start at kind of the leading edge of the main updraft, and then they deepen and strengthen as they move a little bit downwind and beneath the plume, and the top of the vortex kind of tracks along with the primary axis of the plume above. We can see that plume has a bent over structure and then actually subsides as the ashfall region, as the ash is falling back toward the surface. And the top figure shows kind of a conceptual model for this based on laboratory experiments of a bent over plume and crosswinds, which has a number of different characteristic vortex morphologies, including this primary counter-rotating vortex pair, which is clearly evident here, as well as the shedding or wake-like vortices that are pendant from the underside of the plume. And I would argue that you can really see both of those in those vortex morphologies at the bottom. The right panels show these characteristic flow signatures, and also a schematic from laboratory take experiments of a jet and a cross flow that will deflect the incident wind. Those are the red areas around the edges of the jet. Create a flow reversal region, that's the blue arrow behind the jet. And then in this case, where they've broken the symmetry of a curved wake-like region. So if we kind of take that concept and apply it to the radar observations, which are shown above, we see the curved ashfall region, an enhancement of the reflectivity on one flank of this fire. We also see on the right panel the flow splitting and the flow reversal signature. And it's there in the time mean. So that's about an hour-long mean radar signature. And so it's a persistent mean signature, not a kind of transient signature. And then if I plot all the vortex locations, those are the black triangles. There's a whole subset of them that occur in the head fire and the anticyclonic flank of the head fire. And then there's a subset that are the trailing vortices that occur right along the shear zone between the flow reversal and the flow splitting around the fire. All right, next slide, please. 2020 being 2020, a few weeks later, we had another remarkable pyrogenetic tornado event, and this is with the Creek Fire. It's been talked about in a number of previous talks on the 5th of September. Once again, we're looking at a radar animation of the rapid plume development in advance of the fire as it moved up and out of the San Joaquin River drainage. On the right, we can summarize that with a radar reflectivity time height series as we did before. And what's really remarkable here is the plume depths. We once again start out around 6 kilometers, but here we reach things that are around 17 kilometers in depth during the most intense phase of the fire. And throughout that period, we have strong vortices occurring inside and beneath the fire, and then even a second vortex event and pyro-CB event after dark that night. So really a remarkable event that we're just kind of looking under the hood of now. But you can see from these animations, the radar data are extremely rich in describing the evolution of the fire. Next slide, please. Just kind of an overview of where that vortex was in here. The right panel is showing the isosurfaces and the vortex lines. The vortex was, in this case, an embedded vortex within the anticyclonic splitting portion of the plume. You can kind of see this plume bifurcation going on there. The right branch of that is the cyclonic branch, the left, the anticyclonic. The top of that vortex reached up to about 15,000 feet. So these are very significant features. And at the top sequence of panels, we can see some of the same flow characteristics, the flow splitting, the flow reversal, and in this case, once again, an anticyclonic vortex along that kind of looker's left flank of the fire. Next slide, please. We had even another event with the bear fire, which has also been talked about. And what this has really allowed us to do is develop kind of a conceptual model, which you're looking at here, where we're looking at all three fires, the Loyalton Creek and Bear Fire, with the radar reflectivity signatures and the time mean radial velocity signatures. And you have to kind of turn your head because the wind flows in different directions in each of these, but they all have the same characteristics. They all have a plume and a cross flow, a bifurcating plume with counter-rotating vortices, wind shear across the lower half of the plume, rapid vertical growth due to pyro-CB development. And those features show up as key radar signatures with the high intensity head fire associated with the updraft. That's the high reflectivity core, the curved ashfall region, which is indicative of environmental wind shear, as well as flow splitting and flow reversal. And I've really highlighted the flow splitting and flow reversal because I think it's a really key aspect of this. So that's kind of the key points of the talk today, but I just wanted to go to one more slide. The next slide, please. Some other things that we can do with these radar data that pertain to some of the talks that we saw yesterday, we can develop a tracking algorithm which links the high reflectivity cores to the active perimeters of the fire. We can track fire progression at roughly 10-minute intervals and spatial resolutions of about 250 meters. And so that's being applied here for both the campfire on the left and the bear fire on the right to give you a sense, again, for the richness of these data in describing the fire environment. So with that, that's all I have for today. Thanks, Craig.
Neil, thank you. Wow, that's awesome. I'm gonna have people put chat questions in there, but I want to ask one quick question. That flow splitting signature, we see that in very small grass fires too. And so, I mean, that's scaling up to these large fires.
Yeah.
That's pretty exciting.
Yeah, exactly. I mean, it's really characteristic of the fire environment. Once you get a low enough pressure perturbation in the fire, it's going to reverse the wind flow. But it's not always there in the big fires, and then suddenly it's there, and it really does seem to trigger some of these important changes. But yeah, how you go from just the flow split to upscale to these tornadic vortices, I think the wind shear is going to be an important component and something we're looking at.
Fantastic. Thank you so much. Everyone, please ask questions in the chat Q&A, and we're going to go to our last talk. Okay, I'd like to introduce Klaus Scott from the California Air Resources Board. He's a staff air pollution specialist in the Air Quality Planning and Science Division. He leads the developing of the CARB wildland fire emission inventories for regional air quality modeling, and he is the lead for developing the CARB natural and working lands inventory of ecosystem carbon stocks and stock exchange. So, Klaus, please take it away. Thank you.
Okay, and you can hear me okay, everybody?
Yes.
Okay, cool, thanks. Thanks, Craig. Okay, so today I'm going to talk a little bit about my process for building mission inventories for wildland fires. And for those perhaps not familiar with the term, I should probably first explain what an emission inventory is. And in the air quality modeling or regulatory space, an emission inventory is an accounting or a representation of the transfer of trace gases and particles from sources at the surface to the atmosphere. And these sources, of course, include anthropogenic sources, such as industrial facilities in the transport sector, but also natural sources such as wildfires. And so at CARB, emission inventories take the form of reporting. If we go to the next slide, reporting things such as on websites like the one shown here, where if we go to the next slide, We report annual stats, things like totals for acres burned or tons of carbon dioxide emitted. And so that's on the reporting side, but emission inventories also take the form of geospatially and temporally explicit representations for use in regional air quality models. And that's what I'm gonna sort of skate through real quick today. So we can go to the next slide. So the basic task of an inventory for biomass burning is to come up with an estimate of the amount of fuel consumed and how efficiently it was consumed, and conventional approaches to inventory development involve first knowing things like the location and area extent of the fire, the fuel loads associated with the fire's footprint, moisture conditions of the fuels, because these affect flaming and smoldering consumption, which affects chemistry. And then estimating the amount of fuel consumed in those flaming and smoldering phases. And this followed by applying emission factors to the fuel consumption to estimate the emissions of specific pollutant species. And to do that, there are a variety of biomass burning emission models to choose from. Next slide, please. So for this presentation, I retrieved some materials from when I was building a wildfire emission inventory for 2018. And this slide displays the statewide CMAQ model domain. It's 4-kilometer resolution, it extends over a fairly large area. And on top of this, I've also displayed the polygons of the final perimeters of the fires that occurred in 2018. And as we've all seen today, that was a very active year in terms of fire. It's only outdone by last year. And these fire perimeters are a key ingredient in my process for making the inventory. So if we could go to the next slide. So I can use these fire footprints together with the vegetation fuels map then to develop information about the composition and the magnitude of the fuel loads within the fire footprints. And this slide displays the veg fuels raster product I use called FCCS. It's the Fuel Characteristic Classification System developed by the Land Fire Consortium. This product represents over 50 some odd different fuel beds, veg types for California. And so for the rest of my talk, I'm going to be focusing on the campfires as a way to illustrate how I do stuff. So we can go to the next slide. Thanks. Oh, you get animated. Hooray. So we can go to the next slide. It's a close-up. There we go. So in this slide, I've zoomed into the campfire, and this is showing the final fire perimeter, and it's overlaid on this FCCS raster. And we can see there are a variety of veg types across the region. Several veg types occupy a lot of area, such as the ones I've called out here with the arrows. These are forest and woodland types. There's a smudgy area that extends from east of the town of Paradise on up to the northeast, and that is those are light colored areas. Those are that's the old footprint of the BTU lightning complex from 2008. So the fuels along there were very different. So altogether, there are about 45 different fuel load types within that perimeter, ranging from forest and woodland types to veg types dominated by shrubs and grasses. We can go to the next slide. So, so I can tabulate the areas of the amount of area that each fuel bed occupies within the fire footprint. And so on this slide, I'm displaying the top 10 fuel beds by area. And then the top two are, of course, a forest type and a woodland type, followed by a smattering of shrub-dominated systems and some other things. These top 10 account for about 90% of the footprint of the campfire. So we can go to the next slide. And as Susan said, area isn't a great proxy for fuels, but once you do the overlay, in this slide, I've tabulated the fuel beds, I've retrieved the fuel loading information associated with each of these FCCS fuel bed types. And of the top 10, again, they account for about 92% of the total fuel load present in the footprint. And fuel model 16 makes up for about 30% of all the total fuel load. So you can see some veg types present quite a different picture in terms of fuel loads. So that's the story about pre-burn fuel loads. So we can go to the next slide. Then one of the other important ingredients is fuel moistures, and for this work I use a fuel moisture raster product called GridMet. It's developed by John Abatzoglu, who's now at UC Merced. In this slide, I'm displaying the average 1,000-hour moisture for November of 2018. And if folks didn't know, 1,000-hour fuel are dead fuels that have stem diameter greater than 3 inches. And so you can see the moisture varies quite a bit across the region. It's very dry at that time, of course, in the south part of the state, and of course it's cool and wet and whatnot along the coasts. So we can go to the next slide. So you zoom in. So we can see it's very dry. Conditions are very dry in the campfire location for that time of year, and so that's an important input. And we can go to the next slide. So after I've compiled all this information about fuels, I use that to construct a batch input file to FOFM. Using 6.7 at this point, and go to the next slide. Jump into results. So looking at the consumption part, now we can see again the top 10 fuel beds account for 90% of the fuel consumed, and boy howdy, fuel bed 16 there's a lot of fuel that got consumed, and that makes sense. Forests and woodlands, that's where a lot of the fuel is. There's a lot of dead biomass in those kinds of systems, and that's fueling quite a bit of the fire. We can go to the next slide. So, of course, then the emissions are a function of how much fuel is consumed, and this is showing the same top 10 veg types and their contribution to the PM10 emission picture. And I've summed the emissions for flaming and smoldering on here. And again, fuel bed 16, that's Jeffrey pine, Ponderosa pine, Doug fir, California live oak. Veg type is the top performer here in terms of emitting PM10. We can go to the next slide. And then, of course, this is the CO2 emissions picture. And I should say that, of course, PM10 is mostly a product of incomplete combustion, and that's associated with fuels like 1,000-hour fuels and DUF. Well, now we're talking about CO2, and it's mostly associated with flaming combustion, and those are things like your canopy fuels and other things. Again, quite a lot of CO2 emitted by this fire in these top 10, accounting for 90% of the CO2 emissions associated with this fire. And if we go to the next slide. So this is my last slide. So after I do all this stuff, building the emission inventory, then I hand it off to the air quality modeling shop, and they have some other steps to take these emissions and allocate them to the photochemical model grid cells, spatially, and also gin up some plume rise, and then also do some temporal allocation. And we're playing around with a couple of ways to do that, either using day-specific fire perimeters or fire detects, things of that nature. And then they go and they make it, build it into model-ready, CMAQ model-ready files. And that's it. So that's me. I'm done. Thanks.
Great, thank you, Klaus. There's a question on the Q&A. We can have time for one question.
Sure. And the Q&A.
Let me see. So, how can you get a copy of the report there. That's
Oh, sure. Yeah. Hi, Charles. Good to see you.
Great. And I think that's it. So what we're going to do right now is we're going to move on to our panel session. Thank you, Klaus. That was fantastic. And because we're right on time here at 11, I'm going to hand it over to Branko Kosovic, who's going to be the panel moderator and introduce our panelists. This panel session is sponsored by the American Meteorological Society's Ad Hoc Committee on Wildfire Weather, Technology, and Risk. And so we'll hand it over to Branko.
Thank you, Craig. This panel session was organized by the Ad Hoc Committee of AMS, Ad Hoc Committee on Wildland Fire, Weather, Technology, and Risk. And this is a new committee of AMS. And I would like to, as a chair of the committee, I would like to thank Craig and Alex for giving us this opportunity to organize a session as a part of the workshop. Also, I would like to welcome and thank the panelists who were willing to join the session. And panelists are Mark Finney, Mark Brown, Alex Hoon, Tamara Wall. I'll introduce them as they make their statements, and Brian D'Agostino. So we can start with Mark. Mark Finney is a senior scientist, a research forester at the Missoula Lab in Montana, U.S. Forest Service Missoula Lab. And we know him well from his work on understanding the physics of fire spread and modeling of fire spread. And without much ado, I'll give Mark a word to make a statement. I see that based on several questions that we posed to panel in advance of the session. Please, next slide. So these are the questions. I'm not going to read them. You can look at them, and these are the questions that panel members will address. So you can move to next slide. Thank you.
All right. You can hear me okay, right, Branko?
Yes.
All right. Next slide, please. Yeah, Branko asked all of us to address several questions based on our background. And one of them that I chose to address is what is the what are the research needs associated with wildland fire risk reduction? And to me, because the most effective risk reduction technique is for wildland fire is more fire. In most of our fire-dependent ecosystems in the Western United States, we're going to need a lot more fire, particularly in the dry forest. And any kind of tools, any kind of science that supports our ability to conduct those fires with more reliable and predictable results will benefit the risk reduction activities. When I say risk means basically the expected loss or the expected net value change, the way the reinsurance industries deal with it. And so wildfire affects risk by starting large fires, starting a long ways away from where they ultimately end up. And so basically the land needs to be managed upstream, upwind from where the fires originate. And so improved multi-day forecasts, a lot of the smoke modeling that improves the reliability of dispersion estimates can all be helpful in improving the reliability of the application of risk reduction burning. Next slide, please. That's not it. Something got out of order there, Branko.
I'm not controlling the slide.
Cliff's working through it. So let's see here. We have a little technical situation here, but we'll fix it.
We'll fix it. Well, I can continue to speak on it anyway. The other question I chose to address is basically about fire behavior and what are the research needs in fire behavior. Now, this excellent workshop has really shown us a lot of technological advances and advances in computing. But fundamentally, a lot of these models depend on foundational understanding about fire behavior. And there we go. And much of this fire behavior is traditionally characterized according to this scheme of the fire triangle: fuels, topography, and weather. And what I want to talk about is just a few of the many hundreds of open research questions related to each leg of this triangle. Unless we address these fundamental knowledge needs, our models are always going to be beholden to our assumptions and our speculations and our approximations, many of which are decades and decades old. So the next slide, please. So one of which, it sounds very simple, but we still don't know how to characterize fuels properly. We don't know what are the salient fuel properties that need to be known, and then how precisely do we have to know them to make certain accurate calculations. And part of this part of this uncertainty originates with the lack of knowledge about how fires actually spread. So if you don't know the physics of fire behavior and fire spread, you don't exactly know what fuel property to measure. So whether that's large woody material in forested situations or fine material in desert or dry shrub situations, how well do we have to know this and the spatial characteristics of these fuels? Next question, next slide. What is the wind that affects a fire? That's very simple, but winds are highly variable in space and in time. And most of our modeling makes very, very strong assumptions about the winds that are affecting fire. In panel A there, we have wind with a logarithmic profile affecting a backing fire. So the wind is crossing land that hasn't burned yet. Well, we make the same assumption that the profile hasn't changed if it is blowing through the back of a heading fire, so crossing a lot of heated and burned ground, when we know that the boundary layer actually changes for winds as they blow across heated ground. And so panel C kind of shows this boot-shaped wind profile that often is seen from other kinds of experiments. Well, we don't know what is the wind. All of these models depend on understanding the winds that affect the fire. Next slide, please. Slope effects on fire spread. It's already been addressed by one or two speakers in here about how little we know about the effect of terrain on fire growth and fire spread, and the heat transfer process is responsible. But when you increase the slope angle, what happens is there's a dynamical coupling of the plume with the slope, and the plume eventually leans over, attaches to the slope. This includes the flame as well. And that's completely unknown. It's an internal coupled dynamic that needs to be further explored. It has great effects on different fires of different sizes, spreading up slopes, creating different fire shapes. For example, these very pointed shapes on the right that originate from a line ignition, those are not modeled whatsoever by anything. Next slide, please. Convective heating and spreading fires. Convection plays a strong role in transferring heat to fuel particles and igniting them, particularly fine fuel particles. And yet this changes with fire sizes and fire shapes. And we really have had very, very little research to characterize convective heating. Right now, the most accurate way it's done is through computational fluid dynamics, but that's very, very intensive and still dependent on strong assumptions near the ground. So advances in fire modeling would be really advanced much more rapidly if we could understand convective temperature and velocity profiles ahead of these fires. Next slide. Crown fire. Crown fire modeling is still pretty much empirical. It's relying on models and concepts developed in the 1970s with some advancements, but basically the physics of crown fire spread and the role of tree stems, for example, has never been really addressed. Same way with how live foliage burns, whether it's in a crown fire or in a surface fire. Live fuels, their ignition and burning characteristics is largely unknown. Next slide, please. So the final point is related to the interest now in these pyroconvective storms and the role of fuel characteristics in helping create conditions where those form. a lot of our forests now contain tremendous loadings of heavy and deep materials that burn for a long time. And the problem with these things is that they can burn either as smoldering or as they can burn as flaming. And that transition between the two is very poorly known. It has to do with solid phase combustion that's particularly sensitive to ventilation. That is the role of wind. So these fuels can burn for a long time and they can generate huge amounts of energy release or almost none. And that difference depends a lot on the burning conditions. Almost no research in this kind of thing. And if we want to be able to understand pyroconvective storms and their development, we're going to have to focus a bit more on this. Okay, that's it for me.
Whoops, sorry, Bronco, you're muted. Let me unmute you.
Okay. Thank you, Mark. I forgot to mention at the beginning that first every panelist will have a chance to make a statement and then discussion will follow. So the next panelist is Mark Brown. He's a retired deputy fire chief from Marin County Fire Department. He, after retiring, he took a position as officer of the Marine Wildfire Prevention Authority. And through his long career, he was deployed in a number of significant fires in California, from Oakland Hills fire to more recent Camp Kincaid fire and August Complex fire. So Mark, please.
Good morning. I'm super excited to be here. I'll admit to be a little bit intimidated by the level of talent and researchers of the researchers that we have here. And I do want to ask, do you want me to start answering some of the panel discussion questions or just wait?
Yeah, yes, you can address some of the questions.
Okay. Absolutely. So the one that I really want to talk about the most is what are the research operations needs to reduce risk and contribute to improved management and mitigation of wildland fire effects. And the first place I would like to start off with is operational personnel actually need to be more connected with the researchers. And I don't think it's a lack of the researchers reaching out to the operational personnel. I think it's more the operational personnel being open and willing to interact with the researchers and understand what tools are available to them. You know, a lot of us don't understand how much research is going on in the background and how we can absorb that. A lot of it has to do with our ignorance of how the models actually work. And if we don't understand how they work, then we don't necessarily know how they can be improved to help us out. So I think the operational personnel need to start being more aggressive about reaching out and connecting with the researchers. And then yesterday it was mentioned that there has to be trust in the models. And if we don't trust the models, then it's hard to implement them. And there are times where emerging technologies have led us astray. And I won't go into different situations, but I've had situations where a model or IR interpretation has told me one thing and we react to it in that way, and then it ends up being wrong. And we either diminish the confidence that the public has in our ability to handle the fire, or the people that we work for, our agency administrators or our agency administrators' bosses have decreased confidence in us. And then, and this lack of trust sometimes is in the realm of over predicting or sometimes under predicting. And again, much of this is a lot of the science isn't completely digestible to the operational personnel. So if the researchers really can't remunerate the data in a way that we can understand it, then it's hard for us to trust it. It's almost like voodoo. One of my favorite fire behavior analysts would talk about shaking chicken bones, throwing them down on the ground, and that was his predictive model. While he was joking about that, some of the science is about as well understood by operational personnel as that description. And then I think, and I think it's been mentioned quite a bit, is the fire behavior modeling just seems to be behind in the type of fuel conditions that we currently have right now, whether it's from being drought-stricken bug kill or 110 years of fire suppression creating just an immense fuel loading. And it seems that the data isn't being updated for the fuels often enough. And so I wonder if we need to have more frequent LiDAR runs or whatever, but it just doesn't seem like the fuel models have the accurate fuel modeling in order to create accurate descriptions. And then for research purposes for the fires that are turning into urban conflagrations, fire modeling within homes or communities. I know it's got to be tremendously difficult to try to figure out how the fires will run through homes, whether it's the wind eddying because of the homes, the terrain, what type of home is it, what type of ember broadcast is it going to have, what type of defensible space has occurred. But that is a big hole, I think, in our modeling. And I think the other piece that I'll touch on is what is our biggest gap in our response? I think once we get into a major attack and we have the incident management infrastructure there to support us, we have tremendous assets. One of the other questions was there anything lacking from the IMETs or the F-bands? And I'd have to say that I really didn't experience that because I was always coupled with awesome IMETs and F-bands, and it was up to me to learn how to utilize their talents, ask the right questions so I can make better decisions. It's more in the initial attack and the extended attack, and being able to gather intelligence, whether it's because it's night and we don't have air attack, or maybe the smoke column has covered up the fire progression and air attack can't provide us that data. So we need to be able to have some ongoing instantaneous data about where the fire is running so we could start getting our resources out ahead or evacuating people. And then spot weather forecasts that get down into the micro level rather than the macro level. We typically know what the type of prevailing winds we're going to have, but how the terrain, the fuels, maybe, or even the homes are going to affect that weather could be very advantageous for us. I know this is being worked on, but on the spot, quick fire predictions, fire behavior predictions. And then the last piece I'll touch on is in the incident command post with all the data, the tools, and everything else that's available. You need another person in the command post just about to be able to manage all this data. It's hard to manage all the resources you have coming and then be able to weed through all the potential data that's being able to come through to you. And we already know that we're stripped or strapped for personnel on our command post, but you almost need someone standing next to the incident commander or their operations section chief if you have that lit up during the initial attack phase to help us with that. And the last piece, I guess I'll say, is that you asked, is it possible to combine the research during fire operations? And I say absolutely, it's possible. However, you're going to have to get the incident managers to value that and to take the time and to invite and incorporate, because it is an extra workload on the incident management personnel. And sometimes they're going to be resistant to it. But if we keep, as the incident managers, keep complaining about not having good data, well, then we need to do our part and reach out to the researchers and invite you to our incidents so we can have that ongoing data. Thank you very much.
Thank you, Mark. This is great. And as you can see, we have a span of expertise in this panel from research to operations. And that's our goal, to bring the communities together to talk and address these issues so that we can improve both science and operations. So the next panelist is Tamara Ball. She's Associate Research Professor at the Desert Research Institute in Reno, Nevada. She's also Deputy Director of Western Regional Climate Center. Her research focuses on qualitative and quantitative social science research in climate information use by stakeholders. So Tamara, you have your...
Great. I did turn my camera on. Can you guys see me? There we are. Okay.
Thank you. Thank you.
All right. Well, good morning, afternoon, depending on where you are. Thank you for having me. So I believe, if I'm correct, I'm the only social scientist on the panel today. even on the research side. So I was overlooking the questions posed, and I was like, I'm not an operations person. So I kind of had to take a big step back. So I kind of took a big picture look at the gaps and needs. And where I really focused on was the R2O to reduce risk and, contribute to management and mitigation. And when I think about risk, I think about risk to the human population and the built infrastructure, as well as, wildlands and production landscapes. So just what I think would be enormously helpful if we wanted to really improve the R2O operations side of things. I really agree with Mark Finney that I think there needs to be more interaction between operations and the research side. I also think there is an onus on the researchers to be good collaborators, right? And for us to do training with our researchers and our early career faculty on how to be good collaborators. But overall, I think recognizing the complexity of the system that we are trying to have impact on is just hugely important. And we're trying to look at lands through production landscapes, through a whole multitude of different type of intermixed landscapes between the built and the unbuilt environment, suburban, urban landscapes. We have wildfire moving through every one of these at this point. And it's just way more than a feels problem, trying to address this. There's a whole host of socioeconomic, sociocultural, and equity issues that need to be addressed here. And on top of that, we often have what I think right now, especially, are compounding events, that are really stressing all of these systems. So right now, for example, Nevada and much of the Southwest are in drought conditions. On top of that, we have COVID, stressing out the fire management community, which is just after a year of this and last year's fire season, it's hugely just so burned out. Everybody is just at their max right now, in multiple different sectors. But I think the fire management community has just been hit really hard. And we have all the previous wildfire events and experiences from last year, which were often very traumatic as we go into this year. So just recognizing the complexity, I think, and the challenges in this problem space is really important. As we look to try and mitigate this, I think I love the idea of spurning silos. And by silos, I mean all of the structures, the agencies, the entities that we work within that tend to stay within their own silo space instead of building those bridges out. And so it's part of what both Mark and I were mentioning with increasing the collaboration between research to operations. But I think if we really want to address this problem at a societal level, we have to start bringing in urban planners, economists, housing experts, emergency management. I mean, I think the problem space is really vast, and fuels and fire management is only one component of that. And then lastly, I'm always a huge advocate for long-term integrated interdisciplinary teams. Most research is done on 2 to 4 year cycles at the max. There are a few rare instances where we have teams that have more long-term funding that work on renewed 5-year funding sources, the RESA teams, the CASC teams, the Regional Integrated Science and Assessment teams that are funded by NOAA. The Climate Adaptation Science Center teams that are funded by USGS, for example, have some longer duration, but the vast majority of research is these 2 to 4 year cycles. If you really want to start pulling in all of these disparate expertises, everything from practitioners and operations through researchers, community members potentially, it takes a long time to really develop a vocabulary, understanding, and trust. And so what I see happen over and over again is we have teams that get pulled together for a 2-year project, and right as they're really starting to build that trust and that shared vocabulary, which is enormously difficult, the project's over. Even if it's a 4-year project and you've gotten some things done, all of that capital is then essentially dispersed once the project is over. And we're kind of just trying to rebuild these over and over again. So how we can, build these long-term, truly integrated interdisciplinary teams that combine a wide, diverse array of expertise and backgrounds, I think is a real challenge for our society. And I'll stop there.
Thank you, Tamara. This is great. Yeah, another very different aspect and view. So the next panelist is Alex Kuhn. He's an incident meteorologist with the National Weather Service in Reno. He's been incident meteorologist for 10 years, and he was in the past deployed at a number of large fires, including Carr Fire in Redding and Paradise Fire in Campfire in Paradise. So Alex.
All right. Good morning, good afternoon, everyone. Can you hear me okay?
Yes, yes.
So, yeah, my name is Alex Hoon. I'm an incident meteorologist, and I'm out of the Reno National Weather Service office. And we have about 80 National Weather Service incident meteorologists all across the country that we deploy to large wildfires, and we actually work with the incident management teams on these fires, communicating the science and basically translating it over to the firefighters and emergency managers, the sheriffs, the people that are making decisions for evacuations and getting people out of harm's way, and trying to translate the science and working hand in hand with fire behavior analysts to be able to get that science over to save lives and property. And unfortunately, I had the opportunity of working on those two fires in 2018 in Northern California. And 2020 seemed to be yet another exceptional fire season as well, not only for California, but also across the West. And so the things that I saw with my experiences, and first of all, I'll talk about the Carr Fire. The Carr Fire it was actually on July 26th of 2018. We were able to actually use high resolution wind models. We were using the Cansack Wharf and the HUR, and using those models, we were able to identify that the winds were going to be increasing, and working together with fire behavior analysts, we also identified that this fire was going to move very quickly outside of the Whiskey Town Reservoir area and then down into Redding. And so thank God we were able to get the word out. They were getting evacuations in place and moving people out of harm's way. Basically, you can see where basically all of the western side of Redding, west of Interstate 5, was evacuated eventually. Now, we knew that we had a high forecast, a high confidence that the fire was going to come down and it was going to move very quickly. The fire behavior analyst knew that he was going to this fire was going to jump over the Sacramento River, which is a very good sized river here in the West, and move into some of the suburb areas of Redding, which was an amazing call. What we didn't know is that this fire was eventually going to form a fire tornado, which was not only a fire tornado, but I mean a fire tornado with EF3 damage. It was rated an EF3 with the damage that we saw was just incredible. And so that was something that we weren't able to forecast. And, something in the future, to be able to, some of the modeling of plume dynamics and how a fire goes from being a ground fire to a plume dominated fire, and then how it transitions to forming fire whirls, extreme fire behavior, and even fire tornadoes in the future. That may be something that we can better communicate as well. Explosive spread rates, something that I've seen, just over my years of working with this, explosive spread rates versus normal spread rates. It seems like there's a threshold there where the fire begins to influence itself, like a positive feedback mechanism, where it just, it begins to outpace any kind of fire modeling that we have. And that's something that I think that when we can better identify those atmospheric and fuels and topography where it transitions from just a normal fire to an explosive fire, an explosive plume-dominated fire, that would be something that would be very valuable to communicate to the fire managers and to the public. I'm going to throw this out there too. The Haynes Index is an old index. It's shaky science. It needs to be updated. We use it tremendously for the fire community to communicate stability and dryness in the atmosphere, but there has to be a better way of communicating the stability and the chances of having a plume-dominated fire growth. The next slide, please. We'll go on and talk about the campfire for a sec. And the campfire, just a few months after the Carr fire, I was deployed out to the campfire, which this one was, tremendous fire. The first 24 hours, grew to over 80,000 acres. It blew through the towns of Concow, Paradise, and Magalia, and destroyed 18,000 structures and killed 85 people within that period of time. And this was such an incredible fire, and the rates of spread that this moved through, not only did it move through so quickly through the vegetation, but then again, something to touch on what Mark said earlier, and who I worked with. Mark was the IC on this fire, and we got to work together on this. There was the fact that it blew through a urban area, the modeling of an urban conflagration. The fact that it was moving through homes and buildings, it was a completely different fuel type than what any of our fuel models have had in the past. So to be able to communicate that, and then not only that, but we had the fact that it moved through so quickly, and they were trying to evacuate 80,000 people within a matter of hours. It created such a situation where the roads were clogged and the fire was burning all around people as they were trying to evacuate. They couldn't get out in time. So the other question that we bring up is and this kind of goes into some of the social science of Tamara, what she's saying. How do we communicate the wildfire threat before there's fire on the ground? It's one thing to say that there's a fire that's coming, but how do we communicate that, ahead of time, the potential that if a fire starts and it moves through the area, this is what could possibly happen within a matter of hours. And we all know by looking at what happened in Paradise, this will happen again. It's just a matter of time that this will happen again. And how do we bridge that gap between the research that we have, this research that is, amazing. We're hearing these amazing talks these last couple of days, and then translating that to the public and to the fire managers and to the emergency management, so that they understand that these are real possibilities, not just pie in the sky, that this may happen, in another universe, but that this may actually happen within our lifetimes. And so how do we bridge that gap from research to actionable data, actionable information that we can give to the people and to the fire managers? So our perspective is very much operational. Not only are we atmospheric scientists, but we are also wildland firefighters as well, and we get to translate that research, that science, to the firefighters. And I will say this, and Mark pointed this out, Mark Brown pointed this out earlier, we are already, our workload is already 100% full. So anything that we get from the research community, and to be able to use it in operations during a wildland fire, when people are already being told to evacuate, homes are burning, people are dying, that sort of situation, the information that we have to translate has to be easy to use, has to be easy to understand, and it must be trustworthy. We have to have stuff that works. And because ultimately we are communicating science to folks that are non-scientists, and we have to get that information to them in an effective manner that they actually do something about it. So that's all I have. Thank you guys, and I'm looking forward to the discussion.
Thank you, Alex. And the last panel member is Brian D'Agostino. Brian D'Agostino is the Director of Fire Science and Climate Adaptation for San Diego Gas and Electric. And as Director, he is responsible for meteorology, fire science, the Community Fire Safety Program, and climate adaptation initiatives. He serves as advisor and former chair of the American Meteorological Society's National Energy Committee, and sits on several advisory committees specializing in climate adaptation and fire science. Brian, and the word is yours.
Well, thank you very much, Branko. Can I get a quick thumbs up if you can hear me?
Yes, yes.
All right, fantastic. Well, good day, everybody. Really appreciate the opportunity to be here to bring the perspective from inside the utility. You know, San Diego, I was the first meteorologist they hired in 2009. And there is the history of catastrophic wildfire in San Diego. Goes back 1970, a power line started a fire in Cleveland National Forest, which burned 186,000 acres, largest fire in California history at the time. And if that same fire were to happen today, it would be that much worse, right? Because we would have 50 years worth of you know, growth and expansion of our population across San Diego. 2003, we had the Cedar Fire. 2007, of course, another power line related fire, the Witch Fire. So that is really where we looked at developing weather infrastructure within the utility so that we can make the decisions. And when you look at the mission that we had 10 years ago and the mission today, it really is the same, right? And that is, we have to see those big events coming. So we live in this world that's pre-ignition, right? Once a fire starts, of course, we do want to model and see if it's going to hit critical infrastructure, but so much of our focus is trying to ensure that we never have that power line ignition to begin with. So we develop fire potential indices, Santa Ana wildfire threat indice. We really have to see that big day coming. And then once we see that big day coming, part of our mission becomes, we, in a sense, because of public safety power shutoff and the need to turn off the electric infrastructure in areas of extreme fire weather conditions, we have to look 72 hours out. And if we're perfect at our job, we're picking out each area that sees extreme fire weather conditions up to 72 hours in advance so that we can notify customers, work with first responders, work with emergency operations centers, and do everything we can to minimize the impact that these extreme weather events are having on our customers. So we continue to strive, and I'm really going to focus on research areas, kind of what we're doing to try to make an exact science out of something that really isn't. But one, it's wind forecast modeling, right? We've got so much data now. We've had a couple hundred weather stations plus reporting 10-minute data now for a decade. So we've got over 1 billion weather observations. So this can now start training AI. So we're looking at improving our wind forecast modeling using AI and linking all those observations to the WRF model. Climate vulnerability assessments, right? Trying to understand the ecosystems, how we're seeing fuel type conversion, what impact that can play in the long run, because we're making 30 to 50 year investments in how we harden the electric infrastructure. So it's not just vulnerabilities today, but trying to understand how that vulnerability is adjusting as we move 30 to 50 years into the future. Fire behavior modeling is the basis of a lot of this. And the next slide is going to dive into that a little bit more. But let's go back just for 1 second. Thank you for that. So that's the fire behavior modeling. Also, there's a lot of work right now in real-time analysis and using AI to do image analysis, both through drones, but remote sensing, right? The integration of satellite, leveraging GOES 17 right now for detection, mountaintop camera networks. That is a real area of focus for us right now. and then outage prediction, right? Being able to anticipate when and if we are going to see potential faults on the electric system. So now moving to the next slide. Really, I want to start at the bottom, because the main point I want to make here is that, you know, weather modeling is the basis for really all of our operations. We run a series of WRF, and then we're continuously looking to improve this, right? The latest version of WRF, integrating, you know, looking closely at land use models, looking closely at the physics within the model. And we're looking at improvements here through integration of things like WRF S-Fire and continuing to advance. But then all the output from WRF is then fed into fuel moisture modeling. So that's how we determine our 1, 10, 100, 1,000-hour fuels, ERC, herbaceous layers. And I'd say this, from my experience, is the single biggest area where we can continue to improve. I think we've heard it in this discussion already, but a better representation of the fuel environment is going to really improve what ultimately feeds into our fire behavior modeling, which is the top row there. And then we run that daily, right? Tens of millions of simulations every day, and that starts pointing to where are the highest risk areas so that we can operate the electric system as safely as possible. I know I kept it quick, but I know we only have about 20 minutes for discussion, so I will leave it there and hand it back to Branko. You're still muted there, Branko.
Thank you. Thank you to all the panel members. And now I would like to open the session for the questions that we have from the audience. And the first question from Joel Curtis is red flag fatigue. How do we overcome that in alerts and operations? So I'm guessing that's for either Alex or Mark Brown.
Well, I can, Alex, if you don't mind, I could talk about something that what I have dealt with, and not as an incident manager, but as a deputy chief that communicates to the public, relaying National Weather Service's red flag warnings. Sometimes it's hard for the public to digest exactly where that red flag warning is impacting. They'll hear the term red flag that's occurring in their home county and automatically assume that it's impacting them, and they don't necessarily dig into the maps to see that their immediate area is not in that red flag area. And then the other piece is, and I don't know how we conquer this, but after the Tubbs fire and then the subsequent fires in the North Bay, every red flag that came up, people thought it was going to be the next Tubbs fire, when it was a dramatically different red flag event. And in the same way that we categorize tornadoes, categorize hurricanes, I almost think we need to categorize red flag events. And we can say this is a category 1 red flag, and that's going to be the worst, or however we categorize it. I think somehow we need to be able to change that messaging.
And awesome comments, Mark. Thank you. The one thing I will say is there is some work being done as to, you know, kind of modernizing the red flag warning and what that looks like going into the future. What that looks like, we're still trying to figure that out. And actually, Tamara is working on a project nationally that she may be able to comment on as well. But one of the things that we're trying to do is implement a red flag warning that is what we're calling it the particularly dangerous situation. It's kind of a higher end red flag warning where it's not just, because there's red flag days where it's critical and the winds and the dryness and, you know, all of that is critical, but it may not be an extreme event. You see, and so there's, you know, just like Mark was saying, like it's a different category, and we haven't categorized it in multiple categories, but we're looking at like trying to set aside those events that maybe only happen once every couple of years. You know, it's a kind of an extreme event that is very unusual for the time of year.
Thank you. And there is actually another question that kind of ties to the first one, and that's from Shannon Chris. It says, how do all And how do you do all that without insurance companies overusing the information and canceling people's policies or making them exorbitant costs? I'm not sure that we can address that question.
Yeah, I can speak, I mean, briefly from a utility perspective. As you can imagine, we spend a lot of time working with the insurance companies, not about insuring our customers, but even insuring the utility ourselves, right? And being able to build that confidence in the insurance folks that, you know, we are able to anticipate these days, we are able to mitigate the risks. So there are many levels, both from the residential point, but then also up into the utility space of being able to acquire and keep insurance in California.
Thank you, Brian. The next question is from Paul Macron. And the question is, how do you decide as a group that the new researchability is ready for operations? I'm guessing this is a question for Martini, but also for other members of the panel.
Well, it's a good question. There are no criteria to say, well, something is ready for distribution or for implementation. Many of the models that are relied on today have been developed over the past 50 years, right? And so they're not new. There's a lot of knowledge about their limitations, but also knowledge about how to overcome those with judgment on the part of experienced analysts. And so we still don't know when or when some condition would arise that we would have a technology that is so compellingly better than what we currently use that we would have to use it, otherwise we'd be negligent. That's never been determined. That's mostly an organizational thing, a decision, right? Because the science may be very good, but the management has never determined how precisely the predictions have to be before they're useful. There's a great deal of judgment involved in interpreting them, and that goes not just for fire, but also for weather. This is mostly a group of meteorologists, right? And there's a lot of different models and a lot of different errors and assumptions in those models, and it's on the part of the analyst to interpret what that means for the specific questions. So I think there's a little bit too much emphasis on improving modeling in a lot of ways. Not that models can't be improved and shouldn't be, but models are never going to be perfect. We can't take the human out of the situation. A lot of these very complicated models have attempted to take analysts completely out of the chain of control or influence. And I think that's a major mistake. People have to be involved in every single step of the analysis, posing the questions, running the models, interpreting them, just like the meteorological community does now. That needs to be replicated for wildland fire behavior prediction too.
I see Tamara has a hand up, so Tamara?
I think it is more qualitative. And as Alex mentioned, for example, Tim Brown and I are working on a set of recommendations that would revamp the red flag warnings and fire weather watches products, in part to be more aligned with the National Weather Service's hazard simplification program, but also to basically tighten up the criteria for issuance to get at those concerns around over issuance. Although surprisingly, I just did a survey in December and only 23% of the respondents said that they felt red flags were over issued in their area, which was quite a bit lower than I was expecting. But I haven't looked at the geographic distribution of those over issuance concerns just yet. But we often prototype our tools beforehand. Actually, Tim and I were just talking with Alex this week on actually being our guinea pig testers for our prototype red flag tool. And we're going to try and enlist several WFOs to help us prototype that and just test it out and see how it goes. And I think having that kind of buy-in from the operations community is really important. I'll stop there.
Thank you. And Mark Brown has a hand up.
Yeah, and I think maybe we could borrow from the military here, and where they bring in a planning team to act like they're the enemy, and they create plans and share that information with the people that are considered the good guys, right? And it would be a bandwidth issue, but perhaps we bring in operational personnel that aren't attached to the planning of the incident and have them embedded with the researchers and start practicing using that modeling, validating that modeling that's on the side and not impacting the current operations. And then you start getting validation for the models, and you start getting trust and developing systems how we can embed that research at lifetime.
That's an interesting suggestion, because really wildfires are not controlled experiments. So we need to create something that's not impacting the operations directly in order to improve.
But the challenge is having the people to do it, though, because we are always strapped for overhead personnel.
Right.
You know, I wanted to make a quick comment. You know, a lot of our atmospheric modeling is going into because there are so many models out there, and each model has its advantages and disadvantages. We've gone to using a lot of ensemble modeling. You know, one model that may have 20 perturbations, and then using an ensemble of ensembles, multiple models doing multiple ensembles, and bringing that in, and then communicating probabilities to the emergency management regarding weather, right? So like we can literally come to a fire planner, fire manager, and say, there is a 70% chance of exceeding, 40-mile-an-hour winds this afternoon, right? Using these probabilities to communicate. Now, how do we do that for fire behavior? And I think that it's getting there. We're going in that direction, and the more that modeling, and not to say that modeling is the end all be all, because it's not. All models are wrong, and there's just it's a human interaction with it. But the thing is, if we had an ensemble approach of fire behavior models, in addition to the weather models as well, we can be able to use that as a way to communicate. There is a certain percent chance that the fire will be here by 1700 this afternoon, or by tomorrow, or whatever. It's a easy, clear way to communicate. And I think that if we were to go down that road, I think it'd be a very big step for operations.
Brian, did you have anything to add? I think earlier you tried to.
No, nothing additional at this point. Just wanted to emphasize two quick points. One, we can't rely completely on the models. There's such an element to trust. I heard it yesterday when they were talking about building indices and other things. There has to be that human, right? And I think Alex was just saying it too, right? I mean, this is a person-to-person interaction, and we have a tool that's helping us have a decision maker make solid decisions. The other thing is the red flag warning, right? We had 11 in our service territory this year. And what I find is additional tools like the Santa Ana Wildfire Threat Index and the Fire Potential Index. These are trying to inform our decision makers of when it's not that apex event. So looking forward to the continuation of the particularly dangerous situations to see how those can help, especially when we're looking at instituting programs like Power Safety, Power Shutoff, right? Because those are high impact operational decisions that can't be treated every red flag the same. So I'll leave it there.
Thank you. There is a comment by Melissa Morkey. Great discussion on social science related in wildfires, and also the chance to bridge the gap between research operations and the communicating across audiences. Much appreciated. Aligns well with wildfire risk information seeking and messaging research I did with my dissertation. And then the question is, what do you see as the next step to fill that gap? To some extent, this was addressed in previous discussion, but maybe there is something to add. don't know.
Branko, what was the gap again? I just missed it a little bit.
The communication across audiences and in particular messaging research and risk information. So the gap between research and operations.
You know, just to quickly respond, I'm always a big proponent of co-production. It's really hard, it's time consuming, it takes more resources, it doesn't always lend itself to publication, and that can be a real problem for early career researchers that are on a tenure clock. But I think it gets back to my initial comments on the importance of these interdisciplinary long-term teams, and they have that social capital of working with each other, and they also have the relationships developed with stakeholders and practitioners, so that the research results that come out are very user-driven and utilizable and actionable. And I'll stop there.
Thank you. And this was actually the last question that we have in question and answer. So I would invite audience to ask more questions if there are additional, there is additional interest. But I would also invite you to ask questions from each other if you have any particular targeted burning questions. Yes.
So I have just one point I'd like to make. We've been talking mostly about emergency response here and prediction in operational circumstances, but there's a lot more to be gained in wildfire modeling and in communication with the public regarding mitigation and pre-fire proactive measures. And I don't think that that's getting the attention at this point. People are very concerned about fires if they're imminent or they're going on. But by then it's too late, really. You know, there's limited decision space, there's limited opportunity to change the outcome. What has to happen is this community and everyone else has to get together and communicate the urgency of being prepared for fire, both people as well as land managers.
Thank you.
Mark, I'd have to agree with you 100%, and that's why I have a new job with the Marin Wildfire Prevention Authority, and that's fully our mission. And while we are not the first people to do what we're trying to do in Marin, I think we are one of the first agencies that's solely focused on wildfire prevention. There's been agencies that have done tremendous work, but that's been a collateral assignment for their agency, whether it's a U.S. Forest Service, National Park Service, CAL FIRE, it's a wing of their division. And when the West Coast starts burning, all the prevention efforts go away because they're all too busy fighting fire, whereas a wildfire prevention authority can keep pounding that. And that's our sole mission. We don't have to worry about responding to incidents. We can just focus on the messaging and getting the response, really driving home the responsibility of our citizens, that they can't just rely on the fire service to come and save them. They have to be part of the solution beforehand.
We have another question from the audience. Ed Orr asks, prescribed burns are becoming much more common. Are researchers interested and poised to participate to conduct independent opportunistic research? Research can provide value added to the burn results. Early coordination can allow a study design to be incorporated into the prescriptions.
Well, I couldn't agree more. I mean, prescribed burning is the solution. The fire problem doesn't go away if the fuels are still there. And this has been known for thousands and thousands of years by Native Americans and Aboriginal people in Australia. And we need to re-engage in that proactive use of fire. And so I know from certainly my research that we need prescribed burning. We need field-based experiments in order to test the scaling of the physical processes that we have in laboratory measurements. And so it's always valuable to take part in prescribed burns to take those measurements. Unfortunately, it takes an awful lot of planning and execution, coordination with a lot of different personnel in order to collect good data.
Does anybody else want to add anything? No? Okay, we have one more question, and this may be the last one because we are right now at 1 o'clock. In my home in Salinas, California, we had a river fire this year. Some areas are more vulnerable to fires than others. Would it make sense to have a risk assessment of neighborhoods? Also, how about something akin to tsunami evacuation routes?
Bronco, I can tackle that one. Absolutely. In fact, a lot of communities have already done that with their community wildfire protection plan. Well, we just issued our updated CWPP for 2020. We were able to use federal grant money to update our LIDAR data to very current data. And we actually did a parcel level risk analysis for each parcel in the county of Marin. And so that is driving the prioritization of our vegetation management projects. And then your question about tsunami evacuation routes. Well, a little bit different for mapping evacuation routes for a wildfire versus a tsunami. We always know which direction the tsunami is going to come from, whereas we don't always know where the fire is going to be coming from or where we want people to go. But we are moving aggressively towards sharing evacuation data prior to the event and using some social sciences on how people absorb data during an emergency. And we are using with the maps called fire clear maps that they're designed to be absorbed during an emergency, easy to understand, and it's not confusing, with multiple evacuation routes. And then when we have the emergency, we'll couple those maps with lifetime notifications and give people routes via Waze, Google Maps, and so on and so forth, and where they need to go.
Thank you. We have 2 more questions. I know we are over time, so I'm not sure if you are able to stay for a couple more minutes, maybe. And Craig, I don't know.
I think what we can do is we could actually respond to those questions. I responded to one of them, and there is a student question to be the last one from Chris. And
Okay.
then from there, we can wrap up.
So the question is, I know the direction of each student depends on their interest and that they want to do in the industry. But the students going into, say, graduate studies, is there anything in particular within the wildfire industry that you think there should be more of a focus on for students? Brian, I think you have interest in that, so maybe.
You know, I do. I'll use the opportunity to plug 2 positions that we're going to be filling here at SDG&E in the next month or 2, but it's numerical weather prediction, right? I mean, this is an extremely data-rich area right now in California. So I think numerical weather prediction is something that we're focused on, data processing, coding, dealing with these large quantities of data are areas of focus for us right now.
Thank you. And I should add, go ahead, Alex.
Oh, yeah, just one quick comment. If I was a student going through college right now and looking to do graduate studies, I would be looking at social science and like how do people understand data when you're giving it to them? Because like we're trying to get people that are, you know, in their homes going about their daily routines and getting them to change what they're doing, not only in case there's a fire on the ground, but actually change their behavior on preparing before a fire comes in. And so having that understanding and knowledge, social science is not something that when I went through college and I got my degree in atmospheric science, we did not go over social science. And I think that that's something that every single meteorologist needs to have. And if you're going to be working in fire or any discipline that in that matter, with regard to weather, you have to understand how people process information and how they are going to act on it in a way that hopefully saves lives and property.
Thank you, Alex. Tamara, did you want to add something to this since Alex brought social science? You're muted.
I love all my physical science colleagues who are converts to social science. I think that's particularly awesome. So.
I'll make a plug real quick. San Jose State has a new wildfire minor with social science requirement with our new wildfire social scientists that we hired. So yeah, we're all getting into it. We all have to figure this out because it's really important. So with that, I'm going to thank the panelists that put this together and was part of our workshop. We had an amazing interaction. It was great information. And I hate to have to end our show and have to end the workshop, but it was great. And I just want to have a final kind of message. So the videos from today's discussion, all the presentations and yesterday's will be posted to those that registered online. So you will get an email that will allow you to see those videos and have access to the content. Again, it's been great to have everyone here from across the globe providing content on the state of the science and fire weather and coupled fire atmosphere, coupled modeling, prediction, fire danger, and everything that we covered in these 2 or 5 sessions, 6 sessions. It was great. And I think that the panel discussion with the experts was just really interesting. It kept everyone engaged, and I thought the questions were great. And so I want to acknowledge the American Meteorological Society for sponsoring that panel session. And if you have questions from the audience, please reach out to the individual members of the panel and the speakers. Their bios are on fireweather.org, and so you can get all the content there. So we're going to kick everyone off and say goodbye and have a good weekend and a good evening and afternoon. So thank you again for participating. We will see you soon for the next Fire Weather Research Workshop, probably 2023, but we might do it next year. So anyways, thanks again. And if you have any questions, please feel free to email me. Take care, everyone.